Hello and welcome to Sleepy Science. What if the universe you see is only the visible skin of something far larger, stranger, and more unfinished than your mind was ever built to imagine? What if space has no known edge? The farther sky is actually the ancient past. The stars are only a small fraction of what exists. And even empty space may be hiding an energy problem science has not yet solved. In this journey, we'll drift through the deepest truths of modern cosmology, from the idea that the universe may be infinite to the strange way space itself can stretch, from black holes that do not behave like cosmic vacuum cleaners to dark matter that shapes galaxies without giving off light, and dark energy that may decide the future of everything. These are not myths, exaggerations, or science fiction shortcuts. They are real questions from astronomy and physics. Questions that reveal a universe far larger than sight, far older than memory, and far less ordinary than the night sky first appears. We'll explore how galaxies are linked across cosmic webs, how dead stars can forge the elements inside your body, how time bends near black holes, why wormholes remain mathematical possibilities rather than proven roads, and why the more we learn about the cosmos, the stranger it becomes. So if you're ready to drift beyond the familiar sky, tap like, hit subscribe, and step into the mystery with me. Because the deeper we look into the universe, the more it feels like reality was never a simple place around us, but an unfinished question we happen to be awake inside. The universe may be infinite, but we can only see a bubble. You are standing inside a bubble so enormous that your mind can barely hold its outline. And yet the most unsettling part is not how large it is, but that it may be only the tiny visible skin of something without any final wall at all. When you look up at the night sky, it feels as if you are seeing the universe, as if those stars and faint smudges of galaxies are the grand total of what exists. But in reality, you are seeing only what light has had enough time to bring to you. The universe is about 13.8 billion years old. And because light does not travel instantly, every telescope is also a kind of time machine, collecting old messages that have been crossing space for millions or billions of years before finally touching our detectors. But this does not mean the farthest things we can see are only 13.8 billion light years away, because while their light was traveling, space itself was changing the distance between us and them. The edge of what we can observe is now roughly 46 billion light years away in every direction, forming what scientists call the observable universe. Not the whole universe, not a physical shell, not a wall where reality stops, but the largest region from which light has had time to reach us since the early universe became transparent. Imagine sitting in the middle of a dark ocean with a lantern in your hand. The circle of water you can see is real, but it is not the whole ocean. It is only the part your light and your eyes allow you to know. The same is true on a cosmic scale. Our observable universe is our lantern circle, our horizon, our bubble of evidence. Beyond it may be more galaxies, more empty regions, more clusters, more patterns of matter, perhaps continuing so far that the word far loses its meaning. And this is where the idea becomes quietly powerful. The universe may be infinite, but we cannot prove it simply by looking, because looking itself has a limit. You can only receive signals that have arrived. Anything farther away than our cosmic horizon is not necessarily unreal. It is simply unreachable by sight. It may exist as fully as your own room exists when the lights are off, but no light from it has had time to enter our little window of awareness. This is one of the first humbling lessons of cosmology. The universe is not the same as the universe we can observe. What we call everything is often just everything available to us. And that distinction changes the emotional shape of the sky. Suddenly, the visible cosmos becomes less like a complete map and more like a sample, a small page torn from a book whose full number of pages may never be known. Scientists try to understand the larger universe by studying the part we can see with extreme care. They measure the cosmic microwave background, the ancient afterglow from a time when the universe first became transparent enough for light to travel freely. They measure how galaxies are spread across space. They examine whether space appears curved, or flat on the largest scales. So far, the observable universe looks very close to flat, and if space is truly flat in the simplest models, then it could extend infinitely. But could is important. Science does not honestly say, we know the universe is infinite. It says something more careful and more fascinating. All the evidence we have is consistent with a universe much larger than what we can see, possibly infinite, but our measurements can only cover our observable region. If the whole universe is finite but unimaginably huge, our local patch might still look flat to us, just as the surface of Earth feels flat when you stand in a field, even though the planet is curved. So infinity remains possible, not proven. A finite universe without an edge also remains possible, though harder to picture. The mistake is to imagine that the observable universe has an outer border like a glass dome, with nothing beyond it. There is no known cosmic wall. There is no sign that galaxies end at our horizon. The horizon is not a place where something special happens to them. It is a limit in us, a boundary created by time, light, and cosmic history. If someone lived in a galaxy near the edge of our observable bubble, they would not feel close to an edge. They would look out and see their own observable universe centered on them, with some regions we can never see and without some regions that are visible to us. This means every observer carries a different cosmic bubble, like each conscious being walking through existence with a private circle of possible knowledge. The universe does not put Earth at the center. It only makes every observer the center of what they can receive. There is something almost tender in that, and also something lonely. We are not trapped because the universe is small. We are limited because information travels at a finite speed and the cosmos has a history. There may be regions so distant that their light will never reach us, not because they are behind a curtain, but because the geometry and expansion of the universe can place them forever outside communication. They may be real, yet permanently silent to us. They may contain galaxies with stars, planets, chemistry, and perhaps even minds looking at their own skies, never knowing we exist, just as we may never know them. And still, this is not a reason to feel cheated. It is a reason to feel the strange dignity of knowledge. We are small but not blind. From one tiny world around one ordinary star, human beings have learned that the sky is not a ceiling, that the Milky Way is not all there is, that even the billions of galaxies we can detect may be only the visible foam on a much deeper sea. We have learned that observation has a horizon, and that mystery is not the enemy of truth. Sometimes mystery is what truth looks like when it is larger than the tools we use to reach it. So when you hear that the universe may be infinite, do not imagine a simple endless hallway stretching forward forever. Imagine instead a reality so vast that the part available to us is only a warm circle of light in a darkness that may have no final shore. Imagine that every star you see, every galaxy in the deepest telescope image, every ancient photon arriving after crossing most of cosmic time belongs to the knowable bubble, not necessarily to the totality. And then let the thought settle gently. Your entire life, every memory, every fear, every hope, every moment of wonder has unfolded inside a small observable island within a possibly endless cosmic ocean. That does not make your life meaningless. It makes it astonishing, because to be finite inside something that may be infinite is not to be nothing. It is to be the rare place where the universe becomes aware of its own horizon. It is to open your eyes from inside the bubble and understand, even softly, that what you can see is not all that exists, and that beyond the edge of sight, reality may continue, quiet, unreachable, and waiting beyond the last light we will ever receive. The farther you look, the further back in time you see. The sky is not showing you what is happening now. It is showing you a collection of ghosts arriving late. Every time you look upward, you are not looking across space only, but backward through time, because light needs time to travel, and the universe does not deliver its images instantly. The moon you see is not the moon exactly as it is at this moment, but the moon as it was about 1¼ seconds ago. The sun on your face is already about 8 minutes old by the time it warms you, meaning that if the sun could suddenly vanish, you would not know right away. For several quiet minutes, daylight would continue as if nothing had happened. Even the planets are delayed messages. Mars may appear to you as it was minutes ago, Jupiter as it was tens of minutes ago, Saturn even farther behind. This is not because your eyes are weak. It is because the universe has a speed limit for information, and light, fast as it is, still has to cross distance. So the farther away something is, the older its image becomes. A star 10 light years away is not simply 10 light years distant. It is 10 years in the past. You are seeing it as it was a decade ago, while on that star, if it still exists, something else may already be happening that you cannot yet receive. And when you look at a galaxy millions of light years away, you are seeing light that began its journey before modern humans built cities, before written language, before many of the familiar shapes of history had appeared. The Andromeda galaxy, visible to careful eyes under dark skies, is seen as it was about 2.5 million years ago. Its light started traveling toward us when early human relatives walked the Earth, long before anyone could name a star, build a telescope, or wonder what a galaxy was. By the time that ancient glow enters your eye, it has crossed a silence so wide that ordinary ideas of now begin to soften. This is the first deep lesson of looking far away. Distance in astronomy is also age. A telescope is not just a magnifying glass. It is a memory collector. It gathers light that has survived across time, light that left its source when the universe was younger, when galaxies were smaller, when stars were forming in different rhythms, when cosmic history had not yet unfolded into the structure we see nearby. This is why astronomers can study the past without traveling there. They do not need a machine that sends a body backward in time. The universe has already sent the past forward as light. Every distant galaxy is a preserved page. Not perfectly preserved in every detail, but real enough to teach us how things once were. When scientists point powerful telescopes into deep space, they are not only asking, what is far away? They are asking, what did the universe look like long ago? This is how we learn that galaxies have changed over billions of years. Nearby, galaxies often appear more settled, more shaped by time, with graceful spirals, older stars, and long histories of collision, starbirth, and transformation. Very distant galaxies, seen when the universe was younger, can appear smaller, clumpier, more chaotic, full of young stars burning fiercely. Their light tells us that the cosmos was not born looking like the night sky we know. It grew into complexity, it aged, it gathered matter into islands of stars, shaped those islands through gravity, and slowly built the grand architecture that now surrounds us. But there is something strange and almost emotional in this. Because light takes time to arrive, the universe does not allow us to see a single universal present. You can look around your room and feel as though everything is happening together. But even there, light from different objects reaches your eyes after tiny delays. The delays are too small to matter in daily life, so your brain smooths them into one moment. In space, the delays become enormous. The cosmos is not presented to us as one fresh, synchronized scene. It is a layered archive. The moon is seconds old. The sun is minutes old. Nearby stars are years old. Distant galaxies are millions or billions of years old. The deeper you look, the more the present turns into archaeology. And because of this, the night sky is not like a landscape spread out before you. It is more like a library where each shelf belongs to a different age. Some pages are recent. Some are ancient. Some were written before Earth had complex life. Some before Earth existed at all. When you understand this, a simple act like looking up becomes more than beautiful. It becomes unsettling in the gentlest way. You realize that vision is never pure possession. To see something is not always to meet it where it is now. Sometimes seeing is receiving what it once was. This is why astronomers are careful with the word "look back time." It means the amount of time light has spent traveling before it reaches us. A galaxy with a look-back time of billions of years is not just distant. It is an earlier version of the universe captured in transit. And when its light reaches our instruments, it may be stretched, dimmed, and changed by the journey. Very distant light can become redder because space has stretched during its travel, like a musical note lowered as the instrument itself expands. You do not need heavy mathematics to feel the meaning of this. It simply means that the light carries a record of its path. Its color, brightness, and pattern tell scientists both about where it came from and what happened to it along the way. From these signals, astronomers can estimate how far back they are looking, what kinds of stars were present, how fast new stars were forming, and how galaxies matured through cosmic time. In a quiet way, light is history with a physical body. It is not a rumor, it is evidence, but this also means that the universe is full of disappearances we have not yet learned about. A distant star might already have exploded, yet its peaceful light may still be arriving. A galaxy may have merged with another, but we still see its earlier form. Some events are already real in their own regions of space, but not yet real to us, because their information has not arrived. This does not make reality unreal. It makes reality local. It means now is not one simple blanket covering everything at once. What is happening there and what is knowable here are separated by distance, light, and time. And perhaps that is why astronomy feels so close to philosophy. It teaches you that awareness always comes late. You are always receiving the world after it has already become something else. Yet instead of making the universe feel unreachable, this delay gives it depth. The past is not gone in the way we usually imagine. Much of it is still traveling. The light from ancient stars is still crossing darkness. The image of a young galaxy is still on its way to future telescopes. Events that ended long ago can still arrive as fresh discoveries, because the universe preserves them in motion. So when you look farther, you are not escaping the present. You are entering a deeper present, one that contains many ages at once. You are standing on Earth, breathing in this moment, while your eyes and instruments collect signals from eras older than memory, older than language, older than the ground beneath your feet. And maybe this is the softest wonder of all. The universe lets you live in one small moment, but look into many. It gives you a body anchored in now and a mind capable of receiving ancient fire. The farther you look, the further back in time you see, and the more you understand that the night sky is not simply above you. It is behind you, before you, around you, and still arriving. Every star is a delayed hello. Every galaxy is a message from an earlier cosmos, and every act of looking up is a reminder that time is not only something you pass through, it is something that travels towards you quietly, patiently, in the form of light. Most of the universe is not made of ordinary matter. If you could gather every planet, every mountain, every ocean, every living body, every burning star, and every glowing cloud of gas into one cosmic scale, you would still be holding only a thin trace of what the universe contains. That is the quiet shock at the heart of modern cosmology. The familiar stuff, the stuff made of atoms, the material that forms your bones, the air in your lungs, the dust on your desk, the iron in Earth's core, the hydrogen inside stars, and the galaxies shining across deep space is not the main ingredient of reality. It is only a small fraction. Ordinary matter, sometimes called baryonic matter, is the kind of matter built from particles that form atoms. It is the matter that chemistry understands, the matter that makes tables solid, water wet, skin warm, stars luminous, and planets real beneath your feet. It feels like everything, because it is everything you directly meet. It fills your senses so completely that your mind naturally mistakes it for the whole story. But when scientists take inventory of the universe, they find something far stranger. Ordinary matter makes up only about 5% of the total cosmic contents. 5%. Almost everything you have ever seen, photographed, touched, named, loved, feared, or studied belongs to the smallest slice of the cosmic account. The rest is not made of atoms in the usual way. A large part behaves like invisible mass, shaping galaxies and clusters through gravity without shining, burning, or reflecting light the way stars and dust do. An even larger part behaves less like material and more like a property of space itself, associated with the accelerating expansion of the cosmos. These are called dark matter and dark energy, not because they are evil or mystical, but because they are not directly visible to us, and their true nature remains one of science's deepest unsolved problems. And this is where the lesson begins to feel almost personal. The universe you experience is not the universe's majority. Your senses evolved to notice ordinary matter, because ordinary matter is what can touch you, feed you, burn you, shelter you, and become you. But reality does not have to be built around what a human nervous system can easily detect. The cosmos is not obligated to be visible. To understand why scientists believe this, you have to look not at what shines, but at what moves. Galaxies spin in ways that cannot be explained by the stars and gas we can count. Galaxy clusters hold together with more gravitational strength than their visible matter should provide. Light from distant objects can bend as it passes near massive regions, and that bending often reveals more mass than telescopes can see. These clues do not show dark matter directly, but they show its fingerprints. It is like watching curtains move in a room where no one is visible and realizing that something unseen is crossing the air. Scientists do not invent invisible matter casually. They are pushed toward it because the motions of the universe demand more gravity than ordinary matter can supply. Yet dark matter is not simply hidden rocks, dead stars, or cold planets waiting in darkness. Ordinary objects of that kind have been considered, tested, and found insufficient to explain the full pattern. Whatever dark matter is, it seems to be something more fundamental, something that interacts strongly through gravity but very weakly, if at all, through light. It may pass through ordinary matter almost unnoticed. It may be flowing through you right now without touching your atoms in any meaningful way. That sounds unreal, but it is not fantasy. It is a serious scientific possibility based on the difference between what gravity reveals and what light reveals. Still, dark matter is only part of the missing majority. The largest share of the universe's total energy budget is tied to dark energy, the name given to whatever is causing cosmic expansion to speed up over time. Dark energy is not ordinary matter hiding in darkness. It is not a cloud or a substance in the everyday sense. It is closer to a mystery about space itself, about why the large-scale universe behaves as though a faint outward pressure is woven into its structure. Scientists can measure its influence, but they do not yet know its deeper identity. This matters because it changes the way you imagine existence. The universe is not mostly stars. It is not mostly galaxies. It is not mostly the glowing beauty we place in photographs. The glowing beauty is real, but it is not dominant. It is the visible handwriting on a page whose paper, ink chemistry, and hidden pressure are mostly unknown. And even within the ordinary 5%, much of it is not arranged into planets and stars. A great deal of ordinary matter exists as thin gas between galaxies, hot plasma in clusters, and diffuse material spread through space in forms too faint for casual imagination. So even the small atomic portion is not mostly the solid world, you know. Matter at cosmic scale is often stretched, heated, ionized, drifting, and nearly invisible. The familiar world is a special condensation, a rare local arrangement where atoms gathered tightly enough to form stars, planets, chemistry, oceans, cells, and eventually a mind capable of asking what everything is made of. This should make you pause. You are made from the minority ingredient of the universe. Yet that minority became conscious. The part that is least abundant became the part that can wonder about the whole. There is a strange humility in that. It means human life is not built from the dominant cosmic substance, but from the small, bright fraction that can form complex structures, stable atoms, living chemistry, and memory. Dark matter may outweigh ordinary matter many times over, and dark energy may dominate the cosmic future, but neither is known to make planets, trees, hands, music, or questions. Ordinary matter is rare in the universal budget, but creatively powerful. It is the universe's small workshop of complexity. And this is why the fact is not merely cold and statistical. It rearranges your sense of importance. You are not central because you are large. You are not powerful because you are made from the majority. You are astonishing because you come from the minority that learned to look back at the majority and admit honestly that it does not yet understand it. Science at its best does not shrink wonder by explaining things. It deepens wonder by showing how much explanation still surrounds every fact. The next time you look at your hand, remember that it is made of ordinary matter, the rare visible language of the cosmos. The skin, blood, bone, and breath you call yourself are built from atoms that belong to only a small share of reality's total content. Around and through that familiar world is a larger universe of unseen influence, gravitational structure, and mysterious energy, shaping the stage without stepping into the spotlight. And perhaps that is the softest lesson here. What is most obvious is not always what is most abundant, and what is most hidden is not always unreal. The universe is not made mostly of the things that meet your eyes. It is made mostly of what your eyes were never designed to see. Yet somehow, from the small luminous fraction, you appeared. A brief arrangement of ordinary matter, awake inside an extraordinary unknown, trying to understand the darkness that quietly holds the stars. The Big Bang was not an explosion into space. The Big Bang did not happen somewhere far away in the dark. It happened everywhere that space would ever become. That one sentence quietly breaks the picture most people carry in their minds. Because the phrase Big Bang makes it sound like a cosmic bomb exploding into an empty room, throwing galaxies outward from a central point, leaving behind a hollow space where the explosion began. But that picture is wrong. There was no empty room waiting outside the universe. There was no pre-existing darkness into which matter flew. There was no central fireball sitting in one location, while space surrounded it like air around a blast. The Big Bang is not the story of stuff exploding through space. It is the story of space, time, energy, and matter, beginning from an extremely hot, dense early state, and then evolving together. It is not an explosion inside the universe. It is the early expansion of the universe itself, and this difference matters, because if you imagine the Big Bang as an ordinary explosion, you will always look for the wrong things. A center, an edge, a direction, a leftover crater in the cosmos. But modern cosmology does not describe that kind of event. It describes a universe that was once much hotter, much denser, and much more compressed everywhere, not just at one point. Every region we can observe today was once part of that early hot state. Every galaxy, every cluster, every atom in your body, every future star not yet born, traces its history back not to a place in space, but to a condition of space. Think of it this way. When you heat metal, it glows not because one tiny corner exploded, but because the entire material has changed state. The early universe was more like that, a condition of everything, not a blast from somewhere. In its earliest moments, the universe was not filled with stars and galaxies. It was a searing mixture of energy and particles, too hot for atoms to hold together, too intense for light to travel freely in the way it does now. As the universe expanded and cooled, simple particles could form stable combinations. Later, the first atomic nuclei formed, mostly hydrogen and helium, with tiny traces of other light elements. Much later, atoms could finally exist, and light could begin traveling through space more freely. Still later, gravity gathered matter into the first stars and galaxies. This is not a myth of creation told through fire. It is a scientific reconstruction built from evidence. The observed expansion of distant galaxies, the ancient microwave glow left from the early universe, and the abundance of light elements that match what a hot early cosmos should have produced. The evidence does not point to a bomb. It points to a universe that has been cooling, thinning, and changing for billions of years. But because human imagination is trained by everyday experience, we keep trying to place the Big Bang inside a familiar scene. We ask, what was outside it? Or where did it explode? Or what direction did everything fly? These questions feel natural, but they smuggle in assumptions that may not apply. Outside is a spatial idea, and the Big Bang is about the origin and evolution of space itself as we know it. Asking where the Big Bang happened is a little like asking where the surface of a balloon begins while the balloon is being inflated. No single point on the surface is the center of the expansion from the viewpoint of creatures living only on that surface. Every point sees other points moving away as the surface grows. The analogy is not perfect because the universe is not literally a balloon, but it helps loosen the wrong picture. Expansion can happen without a central explosion into surrounding emptiness. It can be a change in the distances within the whole system. In the real universe, galaxies are not shrapnel from a blast racing through a cosmic room. They are more like later structures formed inside an evolving space-time. Some galaxies move toward each other locally because gravity can pull nearby objects together. But on the largest scales, distant galaxies tend to be carried apart by the expansion of space. This is why the Big Bang model is not simply about the past. It explains the structure of the present. It tells us why the universe looks broadly similar in every direction on large scales, why distant galaxies show signs of cosmic expansion, and why there is a faint, ancient radiation coming from all directions, not from one special spot. If the Big Bang had been an explosion in space, you might expect a direction, a center, a pattern of debris moving away from a location. But the ancient afterglow surrounds us because it comes from the early universe as a whole. It is not the light of an explosion seen from outside. It is the cooled remnant of a time when the entire observable cosmos was hot and dense. And this is where the idea becomes quietly humbling. You are not looking back toward the Big Bang by pointing in one direction. In a deep sense, every direction points back toward the early universe, because every line of sight reaches into a time when the cosmos was younger, hotter, and less structured. The beginning is not hidden behind one constellation. It is woven into the background of every direction you can look. Even the matter inside you participates in this story. The hydrogen in your body has roots reaching back to the early universe. The heavier elements in you were forged later inside stars and stellar explosions, but the first simple ingredients were part of the universe's earliest chemical inheritance. So the Big Bang is not merely something that happened back then. It is the first chapter of the physical history that eventually allowed galaxies, stars, planets, oceans, cells, and thoughts to exist. It is not a bang you could have heard, because sound needs a medium and an observer in a familiar environment. And the early universe was not a room with air carrying a shockwave. It is not a flash you could have watched from outside, because there was no outside viewing platform. It is a limit of our cosmic memory, the earliest hot, dense phase our science can describe with confidence, before our current theories become uncertain at the most extreme conditions. That uncertainty matters. Honest science does not claim to know every detail of the first instant, or what, if anything, came before in a way that makes sense. The Big Bang model is not a complete answer to why there is something rather than nothing. It is a powerful description of how the universe developed from an early, hot, dense state into the vast, cool, structured cosmos we observe today. And maybe that is more beautiful than the false image of an explosion. An explosion destroys order outward from a point. The Big Bang story gives us something stranger. A universe that begins not as a firework in space, but as space itself in a radically different condition, expanding, cooling, allowing complexity to unfold slowly from simplicity. So when you hear the words Big Bang, try not to imagine a blast in the distance. Imagine every point that exists today, once belonging to a hotter, denser, younger cosmic state. Imagine no center, no outside room, no cosmic crater, only the entire fabric of reality changing together. And then let the thought settle softly. The universe did not begin as an object thrown into emptiness. It began as the stage and the actors emerging in the same story. You are not a spectator standing far from that beginning. You are made from its consequences. You live inside its expansion. You are a late, quiet expression of a universe that did not explode into space, but became space large enough for wonder to appear. Space itself can stretch. Nothing in your daily life prepares you for the idea that distance itself can grow while nothing is flying through it. You are used to motion as something that belongs to objects. A car moves down a road. A bird crosses the sky. A boat drifts across water. The road stays the road, the sky stays the sky, the water stays the water. But on the largest scales of the universe, something much stranger is happening. Space is not just a silent background where galaxies happen to move. Space can change. Space can stretch. And when it stretches, the distance between very distant galaxies can increase, even if those galaxies are not racing through space like sparks from a fire. This is one of the deepest shifts in modern cosmology, because it asks you to stop imagining the universe as a giant empty container and start imagining space itself as part of the story. Not a stage built once and left alone, but a dynamic fabric whose shape and scale can evolve. When astronomers say the universe is expanding, they do not mean that every object is being pulled apart like rubber in your hand. Your body is not expanding. Earth is not expanding. The solar system is not slowly swelling because space is stretching. At smaller scales, gravity, electromagnetism, and the forces holding matter together are much stronger than cosmic expansion. So atoms stay atoms, planets stay planets, and galaxies can remain bound. The stretching of space becomes important across enormous distances, especially between galaxy clusters that are not tightly tied together by gravity. Think of dots marked on the surface of rising dough. The dots themselves do not need to crawl across the dough, yet as the dough expands, the spaces between faraway dots grow. That picture is not perfect, but it helps you feel the idea. The motion is not only through space, it is also in the changing scale of space. This is why distant galaxies tend to appear as if they are receding from us, and the farther away they are, the faster their distance increases. The relationship was first understood through observations of galaxies whose light was shifted toward redder wavelengths. That redshift is one of the great clues. Light travels as waves, and as space stretches while the light crosses the cosmos, those waves stretch too. By the time the light reaches us, it has been lengthened, reddened, softened by the expansion it has endured. In this way, a beam of ancient starlight becomes a messenger not only from a distant place, but from a changing universe. Its color carries the memory of space stretching beneath it. This does not mean the light got tired, as people once speculated. It means the universe changed while the light was in transit. And that difference matters, because it turns the sky into evidence. The redness of distant galaxies is not just a visual detail, it is a record of cosmic geometry in motion. Now pause on that word, geometry. In everyday life, geometry sounds like lines, angles, school books, drawings on paper. But in Einstein's view of gravity and space-time, geometry becomes physical. The shape and behavior of space are not abstract decorations. They influence how matter moves, how light travels, and how the universe evolves. Space is not nothing in the simple way we often imagine nothing. It has structure. It can curve near massive objects. It can expand between distant regions. It can carry waves when massive bodies accelerate in extreme ways. To say space stretches is not to give emptiness a magical personality. It is to recognize that what we call emptiness has measurable behavior. And perhaps this is why the idea feels so strange. The thing we usually ignore turns out to be active. The silence between galaxies is not merely absence. It participates, it grows, it changes the route and the color of light. It shapes what future observers will be able to see. But there is an important caution here. Space stretching is not like a rubber sheet expanding into some surrounding room. That image can help for a moment, but it can also mislead. In cosmology, the expansion is not necessarily into an outside emptiness. It is the increase of distances within the universe itself. The universe does not need an outer wall or a surrounding void for its internal distances to change. A map can be rescaled without its places walking across the paper. The distances on the map grow because the scale changes. On cosmic scales, something like that is happening to the fabric of space-time. This is also why asking, what is space expanding into, may be the wrong question, or at least a question built from everyday intuition rather than cosmic reality. The universe is not required to behave like an object inside a larger box. Its expansion can be an internal change, not an outward journey, and the more you sit with that, the more the ordinary feeling of space begins to loosen. The emptiness between things no longer feels passive. It becomes part of time, history, and fate. The stretching of space also means that the universe is not simply aging. It is changing the conditions under which everything exists. In the distant future, if expansion continues in the way current evidence suggests, many galaxies beyond our local group will drift so far away that their light will become harder and eventually impossible to receive. The universe will not become smaller, but it may become lonelier to any future astronomer living inside a bound island of galaxies. The evidence of the wider cosmos could fade from view, not because it stops existing, but because stretching space places it beyond practical reach. That thought is quiet but heavy. It means knowledge is not only about intelligence, it is also about timing. We live in an era when the universe is old enough to contain rich structure, but not so old that the larger cosmic web has vanished beyond observation. We are awake during a window when space has stretched enough to reveal its story, but not so much that the story is hidden forever. And maybe that is the emotional center of this idea. Space itself can stretch, and because it stretches, light changes, distances grow, horizons shift, and the future sky may become different from the one we study now. You are not living inside a fixed container. You are living inside a cosmic process. The room around you feels stable, and for your life, it is stable enough. But far beyond the comfort of walls, cities, planets, and stars, the deep universe is quietly increasing its separations. The background is moving without walking. The distances are growing without roads. And in that slow, enormous stretching, the universe teaches a strange lesson. Even emptiness is not always still. Even the space between things has a history. Even silence on the largest scale can expand. Some stars are already dead by the time their light reaches us. Some of the stars shining in the sky may be memories wearing the disguise of light. That thought feels almost impossible at first, because a star looks present when you see it. It appears steady, bright, immediate, as if it is hanging there right now above your head, quietly burning in the dark. But a star is not shown to you in the instant it exists. It is shown to you only after its light has finished the journey from its surface to your eyes. And for nearby stars, that journey may take years, while for distant stars in faraway galaxies, it may take thousands, millions, or even billions of years. This means the night sky is not simply a collection of living fires. It is also a cemetery of delayed messages, a place where some lights continue to arrive long after their sources have changed, faded, exploded, or disappeared into a different form. But it is important to be careful here, because the truth is more interesting than the exaggeration. Most stars you can see with the naked eye are inside our own Milky Way, and are relatively nearby by cosmic standards, often hundreds or thousands of light years away, rather than millions. Many of them are long-lived stars, and many are probably still there, still burning in some form, because stars can live for millions, billions, or even trillions of years depending on their mass. The small, dim red stars can last far longer than the current age of the universe, burning slowly and patiently. A star like our Sun lives for about 10 billion years in its main stable phase. But the most massive stars, the brilliant blue-white giants that blaze with extraordinary intensity, spend their fuel recklessly. They can live only a few million years, sometimes less than the time their light needs to cross a large galaxy cluster or travel from a distant galaxy to us. They are cosmic candles that burn hot, fast, and violently. So when telescopes capture the light of massive stars in galaxies millions of light years away, there is a strong chance that many of those individual stars are already gone, not because they were unreal, but because their lives were shorter than the journey of their own light. You are not seeing the star as it is now. You are receiving the announcement of what it once was. This is one of the strangest emotional facts in astronomy. Light can outlive the thing that created it. A star can die, collapse, or explode, and yet its earlier glow can keep moving outward through space, crossing darkness, passing dust, sliding between galaxies, until one day It lands on a mirror, a detector, or a human retina. In that moment, something that no longer exists in the same way becomes visible. The universe does not erase its events instantly. It lets them travel, and stars have many ways of changing after their light begins its journey. A massive star may end in a supernova, blasting its outer layers into space and leaving behind a neutron star or black hole. A sun-like star will not explode like that. It will swell into a red giant, shed its outer layers, and leave a white dwarf behind. Smaller red dwarfs will fade on timescales so long that the universe has not yet had enough time to produce their final endings. So the phrase dead star does not mean one simple thing. It can mean a star has exploded. It can mean it has collapsed. It can mean it has become a remnant. It can mean the bright object we see is no longer shining in the form we observe. Astronomy is full of these delayed identities. A star in a telescope image may be a young hot giant in the photograph, but in its own region of space, long after the light left, it may have already torn itself apart and enriched its surroundings with heavier elements. And this is not just a story about death, it is also a story about creation. When massive stars die, they do not simply vanish. Their explosions scatter elements into space: oxygen, carbon, silicon, iron, and many ingredients that later become planets, rocks, atmospheres, oceans, and bodies. A star's death can seed future worlds. The calcium in your bones, the iron in your blood, the oxygen you breathe, and the atoms beneath your skin are connected to earlier generations of stars that lived and changed long before you existed. So when a star's old light reaches us after the star has died, it is not only a ghost, it is also a record of a cosmic life cycle, a reminder that the universe builds complexity through transformation. The death of a star can become the beginning of chemistry somewhere else. The end of one furnace can become the raw material for another sun, another planet, another living cell. Still, there is a quiet sadness in the delay. You can look at a bright point in the sky and feel as if you are sharing the same moment with it, but you are not. You are meeting its past. If the star changed tonight, you would not know until the new light arrived. If it is 10 years away, the news would take 10 years. If it is 10,000 years away, the sky could keep showing you its old face for 10,000 years after the change. The sky is patient in a way human life is not. It can hold the image of something after the thing itself has moved on. And perhaps that is why stars feel so haunting. They teach you that presence is not always proof of survival. Something can still shine in your world because its message is still arriving, even if its source has already become something else. In a human life, memory works a little like that, though not in the same physical way. A person can be gone. A childhood can be over. A place can be changed beyond recognition, and yet something from it continues traveling inside you. A voice, a warmth, a sentence, a feeling. The universe does this with light. It preserves the past not as sentiment, but as radiation moving through space. And when you understand that, the night sky becomes deeper than beauty. It becomes a layered archive of stellar lives, some young, some aging, some already transformed beyond the image we receive. The stars are not lying to you. They are simply far away. Their light is honest, but it is late. So the next time you look up and see a star trembling in the dark, do not only ask whether it is still alive. Ask what kind of life it had, how long its fire could last, what elements it made, what future worlds its death may help create, and how long its final messages may continue crossing the universe. Some stars are already dead by the time their light reaches us, but their light still arrives with purpose. It tells us that existence does not end cleanly at the edge of an object. It travels outward. It leaves evidence. It becomes part of someone else's sky. And maybe that is the soft lesson hidden in the stars. Even after a fire changes form, the light it released can keep moving, quietly touching worlds it never knew. Black holes are not cosmic vacuum cleaners. A black hole does not hunt the universe like a monster with an endless mouth. It waits, almost silently, and only what comes too close loses the chance to leave. That may be the first image you need to let go of, Because movies and dramatic illustrations often make black holes look like cosmic vacuum cleaners, roaming through space, sucking in stars, planets, dust, light, and anything unfortunate enough to exist nearby. But real black holes are stranger than that, and in some ways calmer. They do not pull more strongly just because they are black holes. From far away, a black hole's gravity depends mainly on how much mass it has, just like the gravity of a star, planet, or any other object. If the Sun could somehow be replaced by a black hole with exactly the same mass, Earth would not suddenly spiral into it. Earth would keep orbiting almost the same path because the gravitational pull at our distance would be nearly the same. The real disaster would be that sunlight and warmth would vanish, not that the solar system would be swallowed instantly. This one fact changes everything. A black hole is not dangerous because it has magical suction. It is dangerous because its mass is squeezed into an extremely small region, creating a place where escape becomes impossible once you cross a boundary called the event horizon. That boundary is not a solid surface. You would not hit a wall there. It is more like a one-way line in the structure of space-time, a point of no return where every possible path forward leads inward. Outside that boundary, however, gravity still behaves like gravity. You can orbit a black hole. You can pass near one and escape if your path is fast and wide enough. Stars can circle the supermassive black hole at the center of our galaxy for years, decades, even longer, without being swallowed, because orbit is not the same as falling. Around Sagittarius A, the black hole at the center of the Milky Way, astronomers have watched stars loop around in tight, fast paths, proving that a huge invisible mass sits there. Yet those stars are not simply vacuumed away. They are guided by gravity, accelerated, bent into dramatic orbits, but not automatically consumed. To fall into a black hole, matter usually has to lose energy and angular momentum, meaning it has to stop moving sideways enough to avoid plunging inward. This is why black holes often feed not by grabbing everything nearby, but by slowly stealing from gas clouds, companion stars, or disrupted material that has been pushed into the wrong kind of path. Matter with too much sideways motion can whirl around instead of falling straight in. It may form an accretion disk, a flattened storm of gas and dust spinning around the black hole. And ironically, some of the brightest objects in the universe are powered by this process. The black hole itself emits no light from within the event horizon, but the material outside it can become incredibly hot as it rubs, compresses, and spirals inward. That glowing disk can shine brighter than entire galaxies in some active galactic nuclei. So a black hole is not seen because it glows like a star. It is revealed by what happens around it. Stars whipping around unseen mass, gas heating into brilliant disks, jets launching from the intense magnetic environment near the feeding region, and light from background objects bending under extreme gravity. The darkness is surrounded by evidence. But even then, black holes do not eat cleanly. They are messy, selective, and limited by physics. Much of the material around a feeding black hole may never cross the event horizon at all. Some of it can be flung away in winds or jets. Some can orbit for long periods. Some can heat up and radiate energy before only a fraction disappears forever. The image of a bottomless drain is too simple. A black hole is more like an extreme gravitational landscape. If you take the wrong path too close to the deep center, you cannot climb back out. But many paths bend around it, circle it, or escape. The danger also depends on size. A small black hole can have fierce tidal forces near its horizon, meaning the difference in gravity between the side of your body closer to the black hole and the side farther away could stretch you violently, a process often nicknamed spaghettification. A supermassive black hole can have a much gentler event horizon because its boundary is vastly larger. You might cross that line without noticing anything locally dramatic at the exact moment, though your future would still be sealed. The horror is not always an instant crushing at the edge. Sometimes it is quieter. After crossing, every direction that once meant away is gone. The future points inward. That is more unsettling than suction. It is not that the black hole pulls you like a vacuum hose from across the cosmos. It is that if you pass the wrong boundary, the universe no longer offers an exit. This is why black holes are not holes in space in the everyday sense either. They are regions where gravity has shaped space-time so severely that escape requires something faster than light, and nature does not allow that. They are not portals by default, not proven tunnels to other universes, not confirmed shortcuts through reality. Those ideas appear in mathematics and speculation, but ordinary astrophysical black holes are understood as collapsed objects with event horizons, surrounded by environments that can be studied through real observations. And the more carefully you understand them, the more beautiful they become without needing exaggeration. Their power is not fantasy. It is enough that a dead massive star can leave behind a region where light cannot return. It is enough that giant black holes can sit in galactic centers and influence the motion of stars. It is enough that matter falling near them can produce some of the brightest signals we can detect. The truth is already strange. You do not need to turn them into cosmic monsters. In fact, seeing them clearly makes them more mysterious, not less. A monster chooses, a vacuum cleaner pulls mindlessly, but a black hole simply obeys gravity taken to an extreme. And that obedience creates one of the most astonishing objects in nature. It teaches you that the universe can hide something, not by making it small, but by making escape impossible. It teaches you that darkness can have weight, that absence can shape motion, that the unseen can organize the visible. So when you imagine a black hole, do not picture a roaming mouth swallowing the stars. Picture a silent boundary in space, patient and precise, surrounded by orbits, heat, bending light, and the faint evidence of matter making its final choices. Black holes are not cosmic vacuum cleaners. They are places where gravity becomes so deep that leaving is no longer part of the story. And perhaps that is why they stay in the mind so powerfully. Not because they chase everything, but because once something crosses too far inward, the rest of the universe can only watch from the outside. The sun is not yellow in space. The sun looks yellow from Earth because your sky is quietly changing the story before it reaches your eyes. You have seen it drawn as a golden circle since childhood, painted yellow in school books, glowing orange in sunsets, blazing like a warm coin above rooftops and fields. So it feels natural to believe that yellow is the sun's true color. But if you could see the sun from space, outside the filtering effect of Earth's atmosphere, it would not look like the simple yellow disk we imagine. It would appear mostly white, intensely bright, almost impossible to look at safely, because the sun produces a broad mixture of visible colors that combine into white light. That may sound surprising, but it is hidden in plain sight every day. The white daylight that fills your room reveals the color of your hands, brightens clouds, and lets flowers show red, blue, violet, and green is sunlight. If the sun were truly yellow in the simple way a painted yellow object is yellow, the world would be tinted much more strongly. Instead, sunlight contains many wavelengths across the visible range, and when they arrive together, your eyes and brain experience that blend as white or nearly white. The reason the sun often looks yellow from the ground is not because yellow is its pure identity, but because Earth's atmosphere acts like a subtle filter. Air molecules scatter shorter blue and violet wavelengths more strongly than longer red and yellow ones. That scattered blue light spreads across the sky, which is why the daytime sky appears blue. Meanwhile, the direct sunlight that reaches your eyes has had some of its blue light scattered away, leaving it slightly warmer in appearance, especially when the sun is lower in the sky and its light must pass through more atmosphere. At sunrise and sunset, the path through the air becomes much longer. More blue light is removed from the direct beam, and the sun can appear orange, red, or deep amber. So the sun's apparent color is not one fixed truth. It is a conversation between the sun's light, Earth's atmosphere, your eyes, and the conditions of the moment. This is where the ordinary sky becomes a lesson in perception. You are not always seeing an object alone. You are seeing the object plus the medium between you and it. The sun above you is not wearing yellow like a shirt. It is passing through a planetary veil that alters the light before it enters your vision. Astronauts outside most of the atmosphere describe the sun as white, and images from space often show a white solar disk unless filters are added for scientific study or visual clarity. Many dramatic solar images are colored artificially, not to deceive, but to make different kinds of light visible or easier to interpret. Telescopes that study the sun may observe ultraviolet, X-ray, hydrogen alpha, or other specific bands of light that human eyes cannot naturally see in that form. And scientists often assign colors to those images so structure becomes clearer. That is why the sun can appear green, red, blue, or gold in different scientific images. Those colors often represent data, not the naked eye appearance. Even the phrase yellow star can be misleading. The sun is often called a yellow dwarf. But that label is partly historical and based on stellar classification, not a simple visual description. In astronomy, stars are grouped by their spectra and temperature. The sun belongs to a class often labeled G-type, with a surface temperature of about 5,800 Kelvin. It is hotter than red stars and cooler than blue-white stars. Its light peaks around the visible range, but a star's peak color alone does not define what the eye sees. Since the sun emits a wide spread of visible light, the combined result is white rather than green. Even though some simplified explanations mention that the sun's strongest visible output lies near greenish wavelengths, your eyes do not isolate only the peak. They blend the whole visible mixture. This is why the real answer is more subtle and more interesting than saying, the sun is green or the sun is yellow. The sun is a hot, glowing sphere of plasma whose broad visible light appears white from space, while Earth's atmosphere often makes it look yellow, orange, or red from the ground. And this small correction teaches a larger truth. Color is not only a property of objects, it is an experience created through light, environment, and perception. A leaf looks green because of what it reflects under available light. The sky looks blue because air scatters sunlight. The sun looks yellow because your atmosphere edits the balance before you see it. You live inside a world where color feels immediate, but color is always interpreted. It depends on the source of light, the surface it meets, the air it crosses, and the visual system receiving it. This does not make the world fake. It makes the world relational. The same sun can be white to an astronaut, yellow to a child drawing on paper, orange to someone standing at sunset, and deep red through smoke or dust. None of these experiences are meaningless, but they are not all the sun's intrinsic color in the same way. They are appearances shaped by context, and perhaps that is why this fact feels gentle but unsettling. Even the most familiar object in your life, the star that wakes the day and warms your skin, is not quite what it seemed. The sun has been above you all along, not as a yellow lamp, but as a brilliant white source filtered by the blue-making air of your planet. Every sunrise is not just the sun appearing. It is Earth's atmosphere painting the light for you. Every golden afternoon is not only the star's warmth, it is your world translating that star into something softer, something your eyes can live beneath. So the next time you see the sun drawn as yellow, do not think of it as completely wrong. Think of it as a human memory of sunlight after it has passed through air. Think of yellow as Earth's version of the sun, not space's version, and let that small shift open something wider in you. Even the things you believe you know best may be shaped by the invisible conditions through which you meet them. The sun is not yellow in space. It is brighter, whiter, and more physically honest than the symbol we carry in our minds. And yet, from here on Earth, the atmosphere turns that honesty into gold. Gravity is not really a force in Einstein's picture. The most familiar force in your life may not be a force at all, but the shape of the invisible path you are already following. Gravity feels simple because it is always there. It holds your feet to the ground, pulls rain from clouds, gives weight to your body, keeps the moon near Earth, and makes falling feel like the most natural motion in the world. You drop a stone and it falls. You jump and come back down. You sit in a chair and feel the pressure of your own weight. Everything about daily experience tells you that gravity is a pull, a downward tug, a force reaching out from Earth and holding you in place. And in ordinary life, that picture works well enough. Newton described gravity as an attraction between masses, and his description is still incredibly useful for predicting falling objects, planetary orbits, tides, rockets, and much of the motion we see in the solar system. But Einstein changed the deeper meaning of the story. In his picture, gravity is not really a force in the same way a hand pushes a door or a magnet pulls iron. Gravity is what happens when matter and energy change the shape of space-time, and objects move through that shaped space-time along the most natural paths available to them. This sounds abstract at first, but the idea begins gently if you imagine motion without interference. If you were drifting far from everything, with no rocket firing and nothing pushing you, you would feel weightless. You would simply continue moving. Einstein realized that free fall is surprisingly similar. When you fall, before the ground stops you, you are not feeling the force of gravity pulling through your body in the way you might expect. You feel weightless, as astronauts do in orbit. Not because gravity is gone, but because you and everything around you are falling together along curved paths. The strange part is that standing still on Earth is not the natural state in Einstein's view. Standing still is what happens when the ground prevents you from following your natural falling path. The floor pushes upward on your feet push on your bones push through your body, and that upward support is what you feel as weight. In other words, the feeling you associate with gravity is often not gravity itself, but the resistance to free fall. That is a quiet reversal of intuition. The chair beneath you is doing more to create the sensation of weight than gravity is directly doing as a felt force. Einstein developed this insight through the equivalence principle, the idea that being in a closed elevator accelerating upward in deep space could feel just like standing on a planet, while being in a falling elevator could feel weightless. This was not just a clever thought experiment. It was a doorway into a new understanding of reality. If acceleration and gravity can imitate each other so perfectly in local experience, maybe gravity is not a conventional force acting inside space. Maybe it is connected to the structure of space and time themselves. From that idea came general relativity, one of the most powerful descriptions of nature ever created. In this view, Earth does not pull the moon with an invisible rope. Earth changes the geometry around it, and the moon follows a natural curved path through that geometry. The sun does not command planets from a distance like a hidden hand. Its mass shapes the space-time around it, and planets move along paths that are as straight as possible within that curved structure. To your everyday eyes, those paths look like orbits. To Einstein, an orbit is not a planet constantly being yanked sideways by a mysterious force in empty space. It is a planet moving freely through curved space-time. Even light, which has no ordinary mass, bends near massive objects because it follows the paths available through that curved space-time. This was one of the early triumphs of Einstein's theory. Starlight passing near the sun appears slightly deflected, not because the light is pulled like a stone, but because the geometry through which it travels is not perfectly flat. The universe is not a rigid stage where gravity acts from the outside. The stage itself bends, and the actors move according to that bending. But you have to be careful with this image because space-time is not literally a rubber sheet sagging in a room. That common picture can help the mind begin, but it is incomplete. A rubber sheet bends because of gravity, so using it to explain gravity can become circular if taken too literally. The deeper point is not that space is a fabric you could touch, but that distances, times, and paths are physically affected by the presence of matter and energy. Clocks run differently in stronger gravitational fields. Light changes its path. Free-falling objects follow natural routes that reveal the shape of space-time. And when gravity is very strong or changes violently, ripples in space-time itself can travel outward as gravitational waves, something scientists have directly detected from massive cosmic events. This means Einstein's gravity is not just poetry, it makes predictions, and those predictions have been tested with extraordinary precision. The orbit of Mercury, the bending of light, the timing of satellites, the behavior of clocks, and the arrival of gravitational waves from distant collisions. Even the GPS in daily life must account for relativity, because clocks in orbit do not tick at exactly the same rate as clocks on Earth. Without correcting for those effects, navigation would slowly drift into error. So this idea, strange as it sounds, is not locked inside a chalkboard or a distant observatory. It quietly helps your phone know where you are. And still, for all its success, Einstein's view invites a deeper kind of wonder. If gravity is geometry, then falling is not just being pulled. It is being guided by the shape of reality. A falling apple, a circling moon, a beam of light skimming past a star, and your own body standing on the ground are all participating in a universe where space and time are not passive emptiness, but active structure. The ordinary feeling of weight becomes a local clue to a cosmic principle. You are pressed against the ground because Earth interrupts the path you would otherwise follow. You are not glued to the planet by a simple downward force in the deepest sense. You are being held away from your natural motion through curved space-time. That thought can make the world feel unfamiliar in the best way. The ground beneath you stops feeling like a static floor and starts feeling like a boundary between your body and the path the universe would let you take. Gravity, in Einstein's picture, is not less real because it is not a force in the old sense. It is more intimate than that. It is woven into the way distance and time behave. It is the quiet grammar of motion. It tells planets how to circle, light how to bend, clocks how to tick, and bodies how to fall. So the next time you feel your own weight, do not imagine only a pull from below. Imagine the Earth shaping space-time around you. Imagine your body wanting to follow a natural path, and imagine the floor gently refusing to let you go. What you call gravity is not merely something acting on you. It is the shape of the world telling you which paths are possible. And every moment you remain standing, you are feeling not just a force, but the hidden architecture of reality holding you in place. There is no absolute up or down in the universe. If the universe could turn you upside down, you would never know which way upside down truly was. You feel up and down as if they are built into reality itself, as if the sky is naturally above and the ground is naturally below, as if every place in existence must secretly agree with the direction your body has learned since childhood. You stand, you drop something, it falls toward your feet, and your brain quietly builds a world around that sensation. Up is where your head points, down is where things fall, and the rest feels obvious. But this obvious feeling is local. It belongs to Earth, to your body, to gravity beneath you, to the inner ear balancing you, to the horizon your eyes use as a reference. It is not a universal law. In deep space, far from a planet, a floor, or a familiar horizon, there is no absolute up or down. There is only direction relative to something else, relative to your ship, your body, a star, a planet, a galaxy, or a chosen coordinate system. This is not just a strange fact about astronauts floating in orbit. It is a quiet dismantling of one of the deepest assumptions your senses make. Down is not a cosmic direction. It is the direction gravity pulls you locally, or the direction acceleration presses you, or the direction your environment teaches your brain to treat as below. On Earth, down means toward Earth's center. But someone standing on the other side of the planet has their own down pointing in the opposite direction from yours. They do not fall off because they are not standing beneath you in any universal sense. They are standing on their own local ground, with their own feet pointing toward the same planetary center from a different side. From your perspective on a flat map, that may look upside down. From the universe's perspective, there is no upside down at all. The idea becomes even clearer when you imagine astronauts aboard a spacecraft. A person can float near the ceiling, rotate their body, and suddenly the ceiling becomes a wall. The wall becomes a floor, and the floor becomes irrelevant. In microgravity, the brain loses the simple instruction it normally receives from weight. This way is down. Astronauts often adapt by using visual cues, handrails, labels, lighting, and the layout of equipment to create an artificial sense of orientation. But that orientation is chosen, not absolute. If two astronauts face opposite directions, neither is truly upside down. They are simply arranged differently inside the same floating environment. The body can learn this, but at first it can feel deeply disorienting, because your balance system evolved on a planet where gravity constantly gives the nervous system a reference. Tiny fluid-filled structures in your inner ear normally help tell your brain how your head is tilted relative to gravity. Remove or soften that cue, and the old map becomes unstable. Your body asks, which way is down? And space answers, compared to what? That question, compared to what, is the key to the whole subject. In the universe, directions are meaningful only when you define a reference. North and south on Earth are useful, but they are not written into the cosmos as sacred directions. They come from Earth's rotation and magnetic field, and even those are not perfectly the same thing. On a globe, north is often printed at the top, but that is a human convention, not a cosmic command. A map could be drawn with south at the top, and the continents would not become wrong. They would only challenge your habit. The same is true beyond Earth. The solar system has a plane in which most planets orbit, but calling one side above the solar system and the other below is just a choice. The Milky Way has a disk, but there is no universal top of the galaxy. From one angle, the galaxy might look like a glowing wheel. From another, a thin luminous band. From another, something tilted, vast, and almost unrecognizable. The galaxy does have structure, spin, and orientation, but orientation is not the same as absolute up or down. You can define coordinates to study it, and scientists do this all the time because measurement needs language. They create systems based on Earth's equator, the plane of Earth's orbit, the center of the galaxy, or other reference frames. These systems are extremely useful, but they are tools, not cosmic truth. They are like drawing lines on the ocean to help sailors navigate. The lines matter because we agree to use them, not because the water was born with them. This is why space images can be rotated without becoming false. A nebula shown one way in a telescope photo might be turned 90 degrees or flipped for composition, and unless the image is being used for a specific technical comparison, it is not suddenly upside down. The object in space does not have a top in the human sense. It has shape, motion, fields, and structure, but no preferred vertical waiting for us to discover. This can feel oddly liberating. So much of human experience is built around vertical hierarchy. Above and below, higher and lower, rising and falling. We use height as metaphor for success, heaven, power, clarity, hope. We use depth for darkness, burial, fear, the unknown. But the universe does not share our poetry automatically. A star is not nobler because it appears higher in your sky. A galaxy is not beneath another in any ultimate moral or physical sense. The language of up and down is born from bodies living on a surface, not from the structure of existence itself. Even falling is local. You fall toward the strongest nearby gravitational center, but in another environment, that direction changes. Near a moon, down means toward the moon. Near Mars, down means toward Mars. In orbit, you may be falling continuously around a planet, but because everything around you falls with you, you feel weightless. Inside a rotating space station, a kind of artificial down could be created by spin, pressing your body outward against the inner wall. But that too would be engineered, not universal. What your body calls down is often simply the direction in which support, gravity, or acceleration gives you a sense of weight. Remove those cues, and direction becomes a decision. This does not make the universe chaotic. It makes it relational. Objects still move according to real laws. Planets still orbit, stars still cluster, galaxies still rotate. But the idea of one final vertical direction, one true cosmic ceiling and floor, disappears. What remains is a universe of frames, perspectives, and chosen references. And maybe that is why this simple fact can feel quietly profound. You spend your life trusting the ground beneath you as if it defines reality, but the ground defines only your local relationship to Earth. Step far enough away, and the categories soften. There is no top edge of space where things are properly upright. There is no bottom of the universe where things collect. There is no grand arrow labeled up, carved into the fabric of everything. There is only your position, your motion, your chosen reference, and the environment shaping what your body feels. So the next time you stand under the sky and feel certain that the stars are above you, Remember that someone elsewhere on Earth is standing under a different sky, pointing in another direction, just as convinced. Remember that astronauts can rotate through a cabin and remake their sense of up with a turn of the head. Remember that maps, images, and coordinates are useful agreements, not universal verdicts. There is no absolute up or down in the universe, and that does not make you lost. It makes you situated. It means your perspective is real, but not final. Your body gives you a direction so you can live, walk, balance, and belong to a world. But the cosmos gently reminds you that every direction is part of a relationship. And sometimes wisdom begins when the universe takes away the flaw and asks you to discover orientation without pretending it is the same as truth. The observable universe has a limit made by light speed. There is a border around everything humanity can ever see, not built from stone or darkness, but from the simple fact that even light needs time to arrive. This is one of the quietest and most powerful limits in cosmology, because it tells you that the universe does not become visible just because it exists. Something can be real, enormous, ancient, full of galaxies, stars, storms of gas, and worlds we will never name, and still remain forever outside our view if its light has not had enough time to reach us. The observable universe is not limited mainly by the strength of our telescopes, though better telescopes do let us see fainter and earlier things. Its deepest limit comes from the speed of light itself, combined with the age and history of the universe. Light is the fastest messenger nature allows for information in ordinary physics. No image, no signal, no news from a distant object can simply appear instantly across cosmic distances. It must travel, and because the universe has only had a finite amount of time to send those messages toward us, our vision has a horizon. This horizon is not a physical wall where galaxies stop. It is not a shell surrounding Earth like glass. It is a boundary of information, the farthest region from which light has had time to reach us since the universe became transparent enough for light to move freely through space. That last detail matters, because in the earliest universe, light did not travel freely the way it does now. The young cosmos was hot and dense, filled with charged particles that scattered light again and again, like a fog so thick that no clear image could pass through it. Only after the universe cooled enough for atoms to form could light begin crossing space without constantly being interrupted. The oldest light we can directly observe is the cosmic microwave background, a faint ancient glow arriving from every direction, not because it is nearby, but because it comes from a time when the universe first became transparent. It is like seeing the surface of a fog bank, not what lies behind the fog. Before that time, the universe is not visible to ordinary light, so even our deepest electromagnetic vision has a kind of curtain at its beginning. Scientists can still infer earlier conditions from physics, particles, patterns, and theory, but with light alone, there is a last visible surface. This means the limit of the observable universe is shaped by more than distance. It is shaped by speed, time, and the changing conditions of the cosmos. When you look outward, you are inside what physicists call a light cone, the region of space-time whose signals can reach you. Everything you can see, measure through light, or receive as ordinary information belongs inside that cone. Everything outside it may exist, but it cannot yet speak to you. And some regions may never speak to you because space itself continues to evolve while light travels. This is not a failure of imagination. It is a boundary built into the way the universe communicates. You can build a larger telescope, place it above Earth's atmosphere, cool its mirrors, sharpen its detectors, and collect light for longer, but no instrument can receive a signal that has not arrived. A telescope can deepen the view inside the accessible universe. It cannot force the unreachable to become present. This is why the observable universe is not the same thing as the entire universe. It is the part of reality that has entered our possible knowledge. The rest is not necessarily hidden by dust or blocked by a wall. It is separated from us by the travel time of information. And the emotional force of this is easy to miss. Human beings often imagine knowledge as something limited by intelligence, courage, or technology. as if every unknown is simply waiting for a clever enough mind. But cosmology teaches a gentler and more humbling truth. Some unknowns are not puzzles in the ordinary sense. Some are horizons. You cannot solve your way past them with sharper eyesight, because the missing information is not late by accident. It is late because the universe is large, light is finite, and time has a history. Imagine hearing thunder from a storm so far away that the sound takes hours to reach you. Except on the cosmic scale, the messenger is light, and the delay can be billions of years. Now imagine there are storms beyond the distance from which any sound could have arrived since your life began. You would not deny they might exist. You would simply admit they are outside your acoustic world. The observable universe works similarly, but on a scale so vast that even the fastest signal becomes a slow traveler. This also changes how you should think about the phrase, edge of the universe. The edge we can talk about responsibly is not the edge of everything, but the edge of observability. It is the point beyond which we have no direct incoming light yet. If an observer lived far beyond our horizon, their observable universe would be centered on them, containing regions invisible to us and missing regions we can see. This does not make them the true center any more than we are. It simply means every observer receives a different cosmic inventory based on what signals can arrive where they are. The universe, in this sense, gives every location its own circle of possible evidence. That circle grows with time, as more light has time to arrive. But it also changes because cosmic expansion can carry some regions away so quickly that their future signals may never reach us. So the horizon is not a simple frozen line. It is part of an evolving relationship between light, distance, and expansion. Some objects whose ancient light we can see today may already be beyond the region from which light emitted now could ever reach us. That sounds contradictory only because human intuition treats visibility as closeness. In cosmology, you can see an old version of something while its present state is already unreachable. The universe allows us to receive ancient messages from places whose current messages may be lost to us forever. That is not science fiction. It is one of the strange consequences of cosmic scale, and there are other messengers besides light. Gravitational waves, neutrinos, and cosmic particles can carry information too, though each has its own limits and difficulties. Gravitational waves also travel at light speed, so they do not break the horizon. Neutrinos can come from very early and extreme events, but detecting and interpreting them is extraordinarily difficult. No messenger gives us unlimited access. Every form of information must obey the structure of causality. The rule that causes and signals cannot simply skip across the universe instantly. This rule protects the order of events. It is the reason the cosmos can have a coherent story instead of everything influencing everything at once without delay. The speed of light is not only a speed limit, it is a boundary maker, a timekeeper, a guardian of what can be known from where. And that is why the observable universe feels so profound. It is not just a map, it is a record of communication. Everything inside it has managed, in some form, to send a signal across the dark and arrive in our small corner of space. Every galaxy image, every ancient photon, every faint background glow is a successful crossing. But around that success is a silence that may be full, not empty. A silence made not of nothingness, but of messages that have not arrived, or cannot arrive, or belong to regions whose stories are forever outside our causal reach. So when you imagine the observable universe, do not picture humanity standing proudly at the center of all existence. Picture instead a small listening post inside a vast cosmic night, receiving whatever the speed of light and the age of the universe allow. The limit made by light speed does not make the universe smaller. It makes our knowledge more precious. It reminds you that seeing is not owning, and observing is not the same as enclosing reality. We live inside a reachable portion of a possibly much larger whole, gathering ancient signals at the edge of what nature permits us to know, and perhaps that is the soft lesson hidden in this cosmic boundary. The universe is not only what exists, but what can reach you. Beyond the horizon may be more reality than the mind can hold. But here, inside the light that has arrived, awareness opens its eyes and learns to be grateful for every message that made the journey. Cosmic expansion makes distant galaxies fade away. One day, the galaxies that now fill our deepest telescope images may still exist, but to future eyes, they will look as if the universe has quietly erased them. This is one of the most haunting consequences of cosmic expansion. Not that distant galaxies are being destroyed, and not that they are simply moving through space like ships sailing away, but that the expansion of space itself can make their light weaker, redder, slower to arrive, and eventually unreachable. When we look into the deep universe today, we see a sky rich with evidence. Galaxies scattered across vast distances, clusters linked by invisible gravity, faint smears of ancient starlight that tell us the cosmos is far larger and older than everyday intuition can hold. But the view we have now is not guaranteed forever. The universe is changing the terms of visibility. As space expands, the light traveling through it is stretched, and stretched light loses some of the energy that makes it easy for our instruments and eyes to detect. A galaxy that once shone in visible light can have its light shifted into infrared, then into longer and longer wavelengths as the expansion continues to pull the wave crests farther apart. It is not that the galaxy itself becomes weak in its own neighborhood. It may still contain stars, gas, planets, and movement, but its message to us becomes diluted by the journey. The light arrives with less punch, less brightness, less immediacy, and there is another effect that makes the fading even more severe. As the universe expands, the photons from distant galaxies do not only stretch, they also arrive more slowly from our point of view. A distant event that once sent out a burst of light may be seen by us as drawn out over a longer time, as if cosmic expansion has slowed the movie. So the galaxy becomes dimmer, both because each bit of light carries less energy, and because the arriving light is spread out over time. To human perception, it is like a voice calling from across a valley, while the valley itself grows wider, the sound deepening, thinning, and arriving in slower fragments. In astronomy, this fading is not a poetic guess. It is part of how expanding space affects observation. Very distant galaxies are harder to see, not only because they are far away, but because expansion changes the light they send. This is why infrared telescopes are so important for studying the early universe. They can catch light that began as visible or ultraviolet radiation from young stars, but was stretched into infrared by the time it reached us. The James Webb Space Telescope was built, in part, to listen in that stretched light, to see galaxies whose ancient signals would be difficult or impossible for ordinary visible light telescopes to capture. In a sense, Webb does not just look farther, it listens to the universe in the lower reddened tones produced by cosmic expansion. But even the best instruments have limits, because the fading is not merely a technological problem. It is tied to the future of the cosmos itself. If the expansion continues to accelerate, as current observations suggest, then many galaxies now beyond our local gravitational family will eventually slip beyond our cosmic event horizon. That does not mean we will suddenly see them vanish one by one like lamps being switched off. The process is gradual and subtle. Their light will become more redshifted, more delayed, and more faint. New light emitted by them after a certain point will never reach us at all. We may continue receiving older light for an immense time, but it will be stretched so severely that it becomes harder and harder to detect, like a message written on paper being pulled wider until the letters blur beyond recognition. Future astronomers, living trillions of years from now in whatever remains of our local group of galaxies, may look out and see a much emptier universe. The Milky Way and Andromeda will likely have merged into a large galaxy by then, along with smaller nearby companions, forming a bound island of stars. But beyond that island, the distant cosmic web may have faded from view. The evidence that galaxies once filled the observable universe could become nearly impossible to recover from direct observation. Future civilizations might see a dark, quiet sky and believe their galaxy is alone. Not because they are foolish, but because the universe has hidden the evidence that we are lucky enough to see now. This is one of the strangest lessons cosmology teaches. Knowledge depends on when you live. We live during a remarkable era, late enough for galaxies, planets, chemistry, and minds to exist, but early enough that the wider universe is still visible. The sky we study is not just beautiful, it is historically available. There is a window of cosmic time in which the universe tells its story clearly enough to be read. In the far future, that story may become faint, red, and incomplete. Even the cosmic microwave background, the ancient afterglow of the early universe, will continue stretching into longer wavelengths and cooling toward practical invisibility. It will not be gone in an absolute sense, but it may become so weak and so stretched that detecting it becomes nearly impossible for observers bound to ordinary methods. Imagine a library where the books are not burned, but the ink slowly fades, the language drifts, and the shelves move farther away each year. That is closer to what cosmic expansion does to the distant universe. It does not need to destroy the galaxies to remove them from view. It only needs to stretch the space between us and them until their light becomes too faint, too red, too slow, or too delayed to carry a usable message. And this gives the night sky a quiet urgency. When we build telescopes, when we map galaxies, when we measure ancient light, we are not just satisfying curiosity. We are preserving a record from an era when the universe is still generous with information. We are catching signals before time, and expansion bury them beyond reach. The galaxies fading away are not disappearing in their own reality. They are disappearing from our possible knowledge. That distinction matters. It reminds us that the universe is not only made of objects, but of relationships between observers and signals. A galaxy can be real and still become unknowable to us. A light can be emitted and still never arrive. A history can exist and still become inaccessible. So when you see deep space images filled with thousands of galaxies, do not think of them only as distant decorations. Think of them as messages arriving during a precious window in cosmic history. Think of every faint point as something the future may lose. Cosmic expansion makes distant galaxies fade away, not because the universe is cruel, but because distance, time, and space-time itself change what can be shared. And perhaps that is the soft, unsettling beauty of it. We are living while the universe is still visible enough to remember its own vastness, while the distant lights are still reaching us, while the great cosmic story has not yet faded into silence. Dark matter does not emit light. The universe may be filled with something that passes through the room around you without ever casting a shadow. That is the strange quietness of dark matter. Not that it is simply black, not that it is made of dust, not that it is hiding behind stars, but that it does not seem to emit, absorb, or reflect light in the ordinary way matter does. A dark cloud of gas can block starlight. A burned piece of charcoal looks dark because it absorbs visible light. A planet can shine faintly because it reflects the light of a star. But dark matter is different from all of these. It is called dark because light appears almost irrelevant to it. It does not glow like hot gas. It does not shine like a star. It does not scatter light like mist. And it does not make itself known by color, reflection, or surface. If you were waiting for dark matter to appear in a telescope image as a black patch against a bright background, you would be looking for the wrong kind of darkness. Dark matter is not darkness painted onto space. It is a form of unseen mass whose presence is inferred because gravity notices it even when light does not. And that distinction is the doorway into one of the most important mysteries in modern science. The universe is shaped by something that seems to ignore the very messenger our eyes depend on. Light is how most astronomy begins. We study stars by the light they release, galaxies by the glow of their billions of suns, nebulae by the colors of their gas, planets by reflected sunlight, and even distant explosions by the brief brightness they send across space. For centuries, astronomy was almost entirely the art of reading light. But dark matter forced scientists to admit that light is not the whole language of the cosmos. Something can be invisible to telescopes and still be gravitationally real. The first clues came from motion. In many spiral galaxies, stars far from the center move faster than expected, if only visible matter is counted. If the galaxy contained only the stars and gas we can see, the outer regions should behave differently. Instead, the motions suggest a much larger halo of unseen mass surrounding the visible galaxy, extending far beyond the bright disk. This halo is not shining, but its gravity helps guide the motion of stars and gas. It is like watching people dance in a dark room and realizing there is an invisible floor pattern controlling their steps. You cannot see the pattern directly, but the movement reveals it. Another powerful clue comes from gravitational lensing, where mass bends the path of light from objects behind it. When astronomers map how background galaxies appear stretched or distorted around a massive cluster, they can estimate where the mass is, even if that mass is not glowing. In some galaxy clusters, the mass revealed by lensing does not line up perfectly with the visible stars or hot gas. One famous example, often discussed in astronomy, is the Bullet cluster, where two clusters have collided. The hot ordinary gas slowed down and interacted, but most of the gravitational mass appears to have passed through with the galaxies, suggesting a component that does not interact strongly with ordinary matter except through gravity. This does not prove every detail of what dark matter is, but it is strong evidence that the missing mass is not simply ordinary gas we failed to notice. It behaves as if it is mostly collisionless, moving through itself and through ordinary matter with very little friction. That is why dark matter is so hard to catch. If it does not interact with light, and if it rarely interacts with atoms, then it can fill space without announcing itself in the ways our senses expect. It may pass through Earth, through walls, through your body, almost as if you are made of open air to it. But almost is important, because scientists do not yet know its exact nature. Dark matter could be made of particles not included in the familiar set that forms atoms. Candidates have included axions, weakly interacting massive particles, sterile neutrinos, and other possibilities, though none has yet been confirmed as the answer. Experiments deep underground, in particle accelerators, and through astronomical observations continue searching for signs. So far, dark matter remains known more by its effects than by direct detection. It is not a settled particle in a jar. It is a gravitational shadow cast by something that refuses to shine. Yet the fact that it does not emit light may be exactly why the universe looks the way it does. Ordinary matter can heat up, cool down, collide, radiate energy, collapse into disks, and form stars because it interacts with light and with itself in rich ways. Dark matter, by contrast, does not easily lose energy through radiation. It does not cool into bright clouds and ignite. It gathers into large diffuse halos, providing gravitational scaffolding in which ordinary matter can later settle. Without that hidden framework, galaxy formation as we understand it would be much harder to explain. Dark matter may be silent, but silence can still shape architecture. It may not form lamps, but it helps arrange where the lamps can gather. This makes the phrase dark matter feel almost misleading. It sounds like a substance of gloom, when really it may be one of the quiet organizers of cosmic structure. It does not compete with stars for beauty. It makes their arrangement possible. It does not decorate the universe. It supports the deep gravitational pattern beneath the decoration. And there is something deeply humbling in this, because human beings are visual creatures. We trust what shines. We trust outlines, colors, surfaces, reflections. We say seeing is believing, as if reality owes us visibility before we grant it truth. But dark matter teaches the opposite lesson. Some of the most important things in the universe do not appear directly to the eye. They are known by consequence, by influence, by the way everything else behaves around them. The hidden can be real. The invisible can be structural. The unseen can hold the visible in place. And if this feels philosophical, it is still grounded in science. Dark matter is not an excuse for ignorance. It is the name given to a pattern of evidence that appears across galaxy rotation, cluster motion, gravitational lensing, and the large-scale arrangement of cosmic structure. Scientists do not know what it is yet, and that honesty is part of the wonder. We know it is not simply lightless in the way a cold rock is lightless. We know it does not interact with electromagnetic radiation the way ordinary matter does. We know it has gravity. We know the universe behaves as though it is there, but its inner identity remains hidden. So when you imagine dark matter, do not picture a black fog drifting between the stars. Picture an invisible gravitational presence, spread through galaxies and clusters, shaping motion without becoming visible, guiding structure without glowing, existing beyond the normal reach of light. It does not emit light, and that is precisely why it changes the way we think about knowing. The universe is not limited to what can shine into your eyes. Much of reality may reveal itself only through the traces it leaves behind. And somewhere in that silence, dark matter waits. Not as a fantasy, not as a monster, but as a real unanswered question holding the visible cosmos in its unseen hands. Dark energy dominates the universe's future. The future of the universe may be decided not by stars, black holes, or galaxies, but by something so quiet that we only noticed it through the way everything else began to drift apart faster than expected. This is the strange power of dark energy. It is not a glowing substance, not a cloud between galaxies, not an ordinary material you could scoop into a container, but the name scientists give to the mysterious influence that appears to be driving the accelerated expansion of the universe. For most of human imagination, gravity feels like the great ruler of the cosmos. It gathers dust into planets, pulls gas into stars, shapes galaxies, and binds clusters together. If you only knew gravity, you might expect the expansion of the universe to slow down over time. Because every galaxy, every cloud, every hidden mass should tug on everything else, gently resisting the outward growth. For decades, many scientists wondered whether the universe would expand forever, more slowly, or eventually collapse back inward if gravity won. But in the late 20th century, observations of distant exploding stars revealed something unexpected. The expansion was not slowing the way many had expected. It was speeding up. Distant galaxies were not merely separating. The space between the largest cosmic structures seemed to be stretching at an increasing rate. To explain that acceleration, cosmologists introduced dark energy, a placeholder name for a deep unknown. And the more you sit with it, the more unsettling it becomes, because dark energy does not dominate by gathering into bright objects or forming dramatic shapes. It dominates by being spread through space itself. In the current best picture, dark energy behaves almost like a property of empty space, something that remains present even where matter is thin and galaxies are far apart. Ordinary matter becomes more diluted as the universe expands, because the same amount of matter is spread through a larger volume. Radiation becomes weaker too, because its light is stretched as space grows. But dark energy, if it behaves like what scientists call a cosmological constant, does not thin out in the same way. As space expands, there is more space, and the dark energy associated with that space continues to matter. This means that over cosmic time, the ingredients that once shaped the early universe become less dominant, while dark energy becomes more important. It is not stronger in the way a storm grows louder. It wins by persistence. Matter fades in influence across widening distances. Radiation cools into the background. But dark energy remains woven into the expansion, quietly becoming the main actor in the universe's long future. This is why it dominates not only the present cosmic budget, but the direction of what comes next. On local scales, it will not tear apart your body, your planet, or the solar system in the standard picture. Gravity and other forces easily hold small systems together. Galaxies that are already gravitationally bound can stay together. The Milky Way and Andromeda, for example, are expected to merge in the far future because their mutual gravity overcomes the general expansion between them. But beyond bound neighborhoods, across the vast spaces between galaxy groups and clusters, dark energy changes the future's mood. Distant regions become increasingly isolated from one another. The universe becomes less like a busy city whose neighborhoods remain in contact, and more like islands drifting into a fog so wide that no message can cross it. This does not happen suddenly. There is no cosmic switch, no instant disappearance, no dramatic curtain falling over the sky. It is slow, patient, and almost unbearably large in timescale. Galaxies outside our gravitationally bound region will recede beyond meaningful communication. Star formation will eventually slow as gas supplies are used up or locked away. The bright age of the universe will fade into a longer, dimmer era, where the great engines of light become rarer. Dark energy does not need to destroy the stars directly. It simply shapes the background conditions of the future, making the universe colder, more separated, and more difficult to connect across. And this is what makes it different from the other cosmic mysteries. Dark matter helps build structure through gravity, but dark energy appears to loosen the large-scale connections between structures. Matter gathers, dark energy separates. Matter remembers closeness. Dark energy gives distance the final word. Yet honesty matters here. Scientists still do not know what dark energy truly is. It may be a constant energy of space. It may be related to a deeper field that changes slowly over time. It may reveal that our understanding of gravity on the largest scales is incomplete. Current evidence strongly supports accelerated expansion, but the exact nature of its cause remains open. That uncertainty is not a weakness in the story. It is the story. We know enough to see that the future is being shaped by something real in its effects, but not enough to say we have touched its inner identity. It is like watching the tide rise in the dark. You can measure the water climbing the shore, but you still do not fully know the moon behind the clouds. Dark energy forces science into humility because it tells us that the dominant influence on the cosmic future is also one of the least understood. It turns the fate of everything into a question mark written across space itself. If dark energy remains constant, the universe may continue expanding forever, drifting toward a cold, dilute future sometimes called heat death, where usable energy becomes scarce and cosmic activity slowly fades. If dark energy changes over time, other futures become possible, some gentler, some more violent, though those remain uncertain and depend on physics we have not yet confirmed. So the deepest truth is not that we know the ending perfectly. The deepest truth is that the ending seems to be controlled by something we barely understand. And maybe that is why dark energy feels so haunting. It is not a monster. It is not a flame. It is not a visible wall rushing toward us. It is more like a silent rule in the background, a hidden preference of space toward widening, cooling, separating. You live in a universe where stars can be born, planets can form, life can think, and galaxies can shine for billions of years. Yet the largest scale future may belong to a quiet acceleration that pulls the great cosmic scenery farther and farther apart. And still, this does not make existence meaningless. It makes the present more luminous. We are living in an era when the universe is still richly connected, when galaxies can still be observed across deep space, when the evidence of cosmic history is still available, when matter has gathered into forms complex enough to ask what will happen next. Dark energy may dominate the universe's future, but it has not erased the fact that, for a brief and extraordinary interval, the cosmos became bright enough, structured enough, and awake enough to wonder about its own fate. So when you hear the words dark energy, do not imagine simple darkness. Imagine the quiet pressure of the unknown, the invisible tendency that may guide the universe toward vast separation. And then remember that every question you ask beneath the night sky is happening before that silence fully arrives. The cosmic web links galaxies across vast distances. The universe is not scattered like dust thrown randomly into darkness. It is woven into a vast hidden architecture, a web so large that entire galaxies are only its glowing beads. When you look at a single galaxy, it can feel isolated, like an island of stars floating alone in empty space. But when astronomers map millions of galaxies across enormous distances, a different picture appears. Galaxies are not spread evenly like sand on a table. They gather into long threads, sheets, knots, and walls, with enormous empty regions between them. From far enough away, the universe begins to look almost biological, not because it is alive in a literal sense, but because its structure resembles a network. Bright clusters connected by filaments crossing at dense nodes, and vast voids opening between them like silent chambers. This is called the cosmic web, and it is one of the grandest patterns science has ever revealed. It is not something you can see by simply looking up at the night sky, because your eyes catch individual points of light, not the three-dimensional structure connecting them. To reveal the web, astronomers had to measure where galaxies are in space, not just where they appear on the sky, and slowly build maps showing depth, distance, and arrangement. When those maps emerged, the universe stopped looking like a simple collection of separate objects and started looking like a connected system. The cosmic web tells us that galaxies have neighborhoods, highways, gathering places, and empty outskirts. It shows that the universe has structure on scales so large that the human mind struggles to hold them, with filaments stretching for tens or hundreds of millions of light years. These filaments are not solid ropes, and they are not glowing bridges in the way a city bridge glows at night. They are enormous regions where matter is slightly more concentrated, where galaxies and gas trace the paths of gravity across cosmic history. At the intersections, galaxy clusters can form, huge gatherings containing hundreds or thousands of galaxies, hot gas, and hidden mass. Between the threads lie cosmic voids, enormous regions that are not completely empty, but far emptier than the dense structures around them. The result is not chaos, it is pattern, and that pattern grew slowly from tiny differences in the early universe. In the beginning, matter was not arranged into galaxies, stars, and clusters. It was spread much more smoothly, but not perfectly smoothly. There were tiny variations, small regions a little denser than others. Gravity, patient and cumulative, amplified those differences over billions of years. Denser regions attracted more matter. Slightly emptier regions lost matter to their surroundings. Over time, the small unevenness became structure. Clumps became galaxies. Clumps gathered into clusters, and the spaces between them stretched into filaments and voids. The cosmic web is therefore not just a shape. It is a fossil of growth. It is the universe remembering its earliest unevenness and letting gravity write that memory into space. This is why simulations are so important. Scientists can start with conditions similar to what we know from the early universe, apply the laws of gravity, include matter and expansion, and watch a virtual cosmic web emerge. The striking part is that the simulated web resembles the real one. That match tells us we are not imagining patterns in randomness. The web is a real feature of cosmic structure. Still, it is not easy to observe in full. Galaxies are the bright markers, but much of the material in filaments may be thin gas that is hard to see directly. Some of this gas may be warm or hot, spread so diffusely between galaxies that it barely glows. Astronomers search for it through subtle signals. Absorption lines in the light of distant quasars, faint X-ray emission, the way matter bends light through weak gravitational lensing, and the distribution of galaxies themselves. Each method gives part of the picture, like touching different parts of a vast object in the dark. Slowly, the web becomes more real. You begin to understand that galaxies are not simply placed in space. They are fed, shaped, and influenced by their position inside this network. Gas can flow along filaments toward galaxies and clusters, helping fuel star formation. Clusters grow at the nodes where filaments meet. Galaxies in dense environments can evolve differently from galaxies in quieter regions, because their surroundings affect their gas, their collisions, their shapes, and their future. A galaxy is not only what it contains, it is also where it lives in the web. That idea is quietly powerful because it moves cosmology away from isolated beauty and toward relationship. The Milky Way is not just a spiral galaxy alone in the dark. It belongs to a local group of galaxies, which belongs to a larger region shaped by nearby clusters, flows, and filaments. Our cosmic address is layered. You live on a planet, around a star, in a galaxy, in a small group, within a much larger pattern of structure that reaches far beyond anything your body can travel. The cosmic web turns the universe into a kind of geography. Not geography of countries, oceans, and mountains, but geography of gravity, density, motion, and time. And what makes it even more fascinating is that the web is not a finished sculpture. It is still evolving. Clusters continue to gather matter. Galaxies continue to move within their environments. Voids can grow emptier relative to their surroundings as matter drains toward denser regions. The universe is not a static picture hanging on the wall. It is a slow unfolding structure, too vast for human lifetimes to notice directly, but clear when measured across cosmic time. If you could rise outside ordinary scale and see the whole pattern, galaxies would no longer look like lonely sparks. They would look like droplets caught along invisible strands, a luminous map of gravity's patience. Yet the beauty of the cosmic web is not only visual, it teaches something deeper about how complexity forms. Great structures do not always require a central planner. They can grow from simple rules acting over long periods, matter attracting matter, small differences becoming larger, motion guided by gravity, gas cooling where it can, stars forming where conditions allow. The universe does not need to arrange galaxies one by one. It lets structure emerge. And perhaps that is why the cosmic web feels both scientific and strangely intimate. Your own life also unfolds inside networks you do not always see. Families, histories, languages, memories, causes, influences. Invisible structures that shape where you can go and what you can become. The universe, at its largest scale, seems to whisper a similar lesson. Nothing exists in pure isolation. Every bright thing belongs to a larger pattern. Every galaxy shines from within a structure older and wider than itself. So when you think of the cosmos, do not imagine only empty space with occasional islands of light. Imagine a vast web of connection, mostly invisible to the naked eye, revealed by patient measurement and careful thought. Imagine galaxies arranged along threads of gravity, clusters glowing at intersections, voids opening like quiet rooms between the strands. The cosmic web links galaxies across vast distances, not with ropes or beams, but through the long memory of matter responding to gravity. And somewhere inside one small strand of that great architecture, on one small planet, near one ordinary star, you are listening. A tiny conscious point within the web, learning that even the largest darkness is not empty of structure, and even the farthest lights may be connected in ways the eye alone could never see. The early universe was hot, dense, and smooth. Before there were galaxies, before there were stars, before there were planets, oceans, rocks, or anything that could cast a shadow, the universe was almost unbelievably hot, crowded, and strangely even. That is one of the most important and easily misunderstood facts about the early cosmos. It was not a place filled with objects the way the universe is today. There were no shining suns floating in darkness, no spiral galaxies turning slowly, no cold, empty spaces between star systems, no planets waiting to form. The early universe was more like an everywhere-filled state of extreme heat and density, a glowing environment where matter and radiation were packed together so tightly that the familiar categories of the modern world had not yet taken shape. If you could somehow imagine being there, not safely, not as a body, because no body could exist in such conditions, you would not see a sky full of separate points. You would be inside something closer to a brilliant, blinding fog of energy, where light could not travel freely for long distances because it was constantly being scattered by charged particles. The universe was opaque, not dark. It was full of light, but that light was trapped in a restless crowd, bouncing again and again, unable to stream cleanly across space the way starlight does now. This is why the early universe is so different from the night sky, you know. Darkness is not the original state of the cosmos. Darkness came later, after expansion and cooling allowed matter to thin out, atoms to form, light to move freely, and eventually stars to ignite in separate places. At first, the universe was hot enough that ordinary atoms could not hold together. Electrons and nuclei moved in a charged plasma, mixed with radiation in a state where everything was interacting rapidly. The word dense here does not simply mean crowded in the everyday sense. It means that the same cosmic contents we now see spread across enormous distances were once compressed into a much smaller volume, making the universe far hotter and more energetic than it is today. But perhaps the strangest part is not the heat or the density. It is the smoothness. When scientists look at the oldest light we can observe, the cosmic microwave background, they find that the early universe had nearly the same temperature in every direction, with only tiny variations. These variations are real and crucial, but they are small compared with the overall uniformity. This means that the infant universe was not a chaotic mess of huge lumps and empty gaps. It was astonishingly even, almost the same everywhere we can measure. And that smoothness is not boring. It is one of the great clues. If the early universe had been wildly uneven, gravity would have amplified those differences too strongly, and the cosmos would not have grown into the balanced, large-scale structure we observe today. If it had been perfectly smooth, with no tiny variations at all, there would have been no seeds for galaxies, stars, and planets. The universe needed both, a deep overall smoothness and small imperfections. The smoothness gave the cosmos a broad, orderly foundation. The imperfections gave gravity something to work with. Those faint irregularities, almost invisible at first, eventually became the beginnings of structure. In that sense, everything you now see, galaxies, clusters, stars, worlds, and the chemistry of life, depended on the early universe being not perfectly uniform, but almost uniform. It is a delicate idea. Too much chaos, and the universe becomes violently clumped. Too much perfection, and nothing grows. The early universe had just enough unevenness to become interesting. The cosmic microwave background is our strongest window into this ancient condition. Today, it is not a blinding glow, because the expansion of the universe has stretched and cooled it into faint microwave radiation, but it still fills the sky in every direction. It is not light from stars. It is not light from galaxies. It is a leftover signal from a time when the universe became transparent, a kind of fossil glow from the moment light could finally travel freely through space. When scientists map tiny differences in this glow, they are reading the texture of the early cosmos. They can see where the universe was slightly denser or slightly warmer, where sound-like waves once moved through the hot plasma, where future structure had its first quiet hints. These were not sound waves in air, because there was no air as we know it, but pressure waves moving through the early mixture of radiation and matter, compressing and relaxing regions of the young universe. The marks of those ancient waves are still present in the patterns we observe today. That is a breathtaking thought. The largest structures in the universe carry traces of vibrations from a time before the first star existed. The early cosmos was not silent in the simple sense. It had rhythms, pressures, interactions, and patterns, but not the kind of sound a human ear could hear. It was physics before scenery, process before objects, and as the universe expanded, it cooled. Cooling did not mean becoming lifeless. It meant becoming able to form new kinds of order. At high temperatures, complexity is often impossible because everything is too energetic to stay bound. As the universe cooled, protons and neutrons could form simple nuclei. Later, electrons could join with nuclei to form neutral atoms. Much later, gravity could gather matter into the first stars. In this way, cooling became creative. The universe did not become interesting by staying violently hot forever. It became interesting because heat gave way to structure, because the dense early state relaxed enough for matter to settle into new forms. There is something deeply humbling in this. The universe you live in, cold enough for atoms, quiet enough for planets, stable enough for life, is not the default beginning. It is the result of a long transformation from conditions that would have erased every familiar object before it could form. Your body is possible because the universe cooled. Your thoughts are possible because the early plasma became atoms, because atoms became gas clouds, because gas clouds became stars, because stars created heavier elements, because later worlds formed from those elements. But the first essential step was that the universe began as a hot, dense, almost smooth state and then changed. So when you hear that the early universe was hot, dense, and smooth, do not let the simplicity of the phrase hide its power. Hot means matter as you know it could not yet exist in stable form. Dense means the cosmos was once packed into a far more crowded condition. Smooth means the universe began with an astonishing large-scale evenness, interrupted only by tiny seeds, from which all later structure could grow. This is not just a description of the past. It is the reason there is a present like ours at all. Before the universe became a place of separate lights, it was a nearly uniform glow. Before it became detailed, it was simple. Before it became full of worlds, it had to become cool enough for difference to survive. And maybe that is the quiet lesson hidden in the beginning. Complexity does not always start with drama. Sometimes it begins with smoothness, with balance, with tiny imperfections almost too small to notice, waiting patiently until time turns them into everything. Tiny quantum fluctuations became cosmic structure. The largest galaxies in the sky may owe their existence to tiny, restless tremors that once lived far below the scale of anything you could ever touch. This is one of the strangest and most beautiful ideas in modern cosmology. The universe's enormous structure may have grown from quantum fluctuations, tiny variations in energy that appeared in the very early universe when everything was still unimaginably small, hot, and young. To understand why this matters, you have to let go of the idea that empty space is perfectly calm. In the quantum world, even what looks like emptiness is not truly dead or motionless. Fields can have small natural jitters, brief variations, tiny uncertainties built into the fabric of physical reality. These are not little sparks flying around like dust. They are subtle fluctuations in the values of quantum fields, a kind of unavoidable restlessness in nature's deepest layers. In everyday life, these effects are hidden from you because the world is large, warm, noisy, and dominated by ordinary objects. A table does not flicker into a galaxy. A room does not visibly tremble with quantum uncertainty. But in the earliest moments of the universe, when the scale of everything was extreme and the conditions were unlike anything around us today, those tiny fluctuations mattered. According to the leading picture, very small quantum variations were stretched to cosmic sizes during the universe's earliest rapid growth. What began as microscopic unevenness became large-scale difference, and those differences, once stretched, did not disappear. They became the faint fingerprints that later guided where matter would gather more easily and where space would remain emptier. This is not saying that a single quantum wiggle directly became one specific galaxy in a simple, cartoonish way. The real story is slower and more layered. Tiny fluctuations created a pattern of slightly denser and slightly less dense regions. After the universe cooled enough for matter to behave more steadily, gravity began to amplify those small differences. A region with just a little more material could pull in more material over time. A region with slightly less could become more empty by comparison. Across billions of years, the smallest early variations became the seeds for the cosmic landscape. Galaxies, clusters, filaments, and vast voids. The universe did not need to begin with fully formed structure. It needed only tiny differences and enough time for gravity to work. That is the astonishing part. The grand architecture of the cosmos did not require a sculptor placing galaxies one by one. It grew from delicate early irregularities, enlarged by cosmic expansion and patiently developed by gravity. We can see evidence for this in the cosmic microwave background, the ancient radiation that carries a record of the young universe's texture. When scientists map it in detail, they find tiny temperature differences spread across the sky. These differences are extremely small, but they are not random noise in the meaningless sense. They form a pattern that matches what we would expect if early quantum fluctuations had been stretched and preserved as the starting points for later structure. In other words, the oldest light we can observe contains a kind of baby picture of the universe. And in that picture are faint marks of the future. Not stars yet, not galaxies yet, not planets, just tiny variations, almost invisible, carrying the potential for everything that would come later. This is where the idea becomes almost impossible to hold emotionally. The Milky Way, the galaxy that contains the Sun, Earth, your home, your memories, and this moment of listening, may trace its deep ancestry back to microscopic uncertainty in the early universe. The same is true of every galaxy cluster, every glowing spiral, every distant island of stars. The modern cosmos is not separate from the quantum world. It may be the quantum world enlarged, cooled, and given time to become visible. That does not mean your life is controlled by random magic. And it does not mean every thought has a cosmic destiny written in quantum foam. It means something more grounded and more profound. The universe's large-scale structure may have originated from real physical fluctuations at extremely small scales. Randomness did not stay small. Under the right conditions, tiny uncertainty became the starting pattern for enormous order. And this is a deeply scientific idea, not just a poetic one, because it makes testable predictions. The pattern of temperature variations in the cosmic microwave background, the distribution of galaxies, and the statistical arrangement of large-scale structure all give scientists ways to compare theory with observation. So far, the broad picture fits remarkably well. There are still open questions, especially about the exact physics of the earliest moments. But the connection between early fluctuations and later structure is one of the strongest bridges between quantum physics and cosmology. It tells us that the universe is not divided neatly into a tiny quantum world and a large cosmic world. The largest things we know may carry the memory of the smallest processes we can describe. A galaxy is not quantum in the everyday sense. You cannot treat a spiral galaxy like a single electron, but the origin of the pattern that helped galaxies form may reach back into quantum behavior. The universe is layered like that. Small rules become large consequences. Invisible beginnings become visible worlds. A difference too faint for any creature to notice at the time can become, after enough expansion and gravity, a cluster of galaxies spanning millions of light years. And there is a quiet lesson in that. We often imagine beginnings as dramatic, loud and obvious, but the universe suggests that beginnings can be almost imperceptible. The first marks of structure were not blazing stars or carved walls of matter. They were tiny variations, nearly smooth, nearly nothing, but not quite nothing. That not quite was enough. Enough for gravity to choose paths of growth. Enough for matter to gather unevenly. Enough for the cosmos to stop being perfectly uniform and begin becoming interesting. If the early universe had been completely smooth in every possible way, there would have been no preferred places for matter to gather. No first steps toward galaxies, no deep structure for future stars. If the fluctuations had been too extreme, the universe might have become chaotic in a different way. What we observe suggests a delicate beginning. Small seeds, widely spread, waiting for time to enlarge their meaning. So when you look at a deep image of galaxies, do not see only finished beauty. See the echo of a beginning that was almost invisible. See quantum uncertainty stretched into cosmic geography. See gravity reading the faintest early marks and slowly turning them into places where stars could form. The universe did not begin with the grand structures we admire now. It began with tiny differences that survived, and perhaps that is what makes the story so haunting. Everything vast may depend on something subtle. Everything bright may begin as something barely there. And somewhere in the ancient tremble of quantum fields, the first quiet instructions for galaxies were already waiting to unfold. Galaxies collide without many stars hitting. When two galaxies collide, the strangest part is not how violent it is, but how much of it passes through itself like a storm made mostly of empty space. The word collision makes your mind imagine impact. Metal smashing into metal, glass breaking, worlds crashing, stars slamming into stars like sparks in a furnace. But galaxies are not solid objects. They are enormous systems of stars, gas, dust, dark matter, and gravity, spread across distances so vast that even a galaxy containing hundreds of billions of stars is still mostly open space. If you could shrink the stars in a galaxy down to tiny grains, the distances between them would be huge compared with their sizes. This means that when two galaxies meet, their stars usually do not hit each other directly. They pass between one another through enormous gaps, like two swarms of fireflies drifting through the same night without many individual fireflies touching. That does not make a galactic collision gentle. It only means the violence happens in a different way than your instincts expect. The true drama is gravitational. As two galaxies approach, their mutual gravity pulls and stretches them, distorting their shapes, bending their spiral arms, pulling long streams of stars outward into tidal tails, and sending waves through their gas and dust. The stars mostly survive as individual stars, but their orbits can be completely rearranged. A star that once moved calmly around the center of one galaxy may be thrown into a wider orbit, pulled into a new structure, or become part of a merged galaxy that no longer resembles either original system. So the collision is not like two stones smashing. It is more like two vast cities of motion passing through each other, while every road, every neighborhood, and every direction of travel is slowly rewritten by gravity. The gas inside galaxies behaves differently from the stars. Gas clouds are spread out, but they can collide, compress, heat, and lose energy more easily. When galactic gas meets other gas, it can pile up and form dense regions where new stars are born. That is why galaxy collisions can trigger starbursts, periods of intense star formation. In images of interacting galaxies, you may see bright blue regions where young massive stars have recently formed from compressed gas. The collision does not simply destroy, it can awaken. It can take cold clouds that drifted quietly for ages and squeeze them until gravity inside those clouds begins building new suns. In this sense, a galaxy merger is both disruption and creation. It scatters old orbits while igniting new stellar nurseries. It tears shapes apart while building future light. Some of the most beautiful galaxies photographed by telescopes are not peaceful objects in perfect isolation, but systems caught in the middle of gravitational transformation. The antennae galaxies, with their long tidal tails, the Whirlpool galaxy interacting with a smaller companion, countless distant merging systems whose distorted shapes reveal encounters that have been unfolding for hundreds of millions of years. These events are slow on human scales. A galactic collision is not a flash. It is a long gravitational dance lasting hundreds of millions to billions of years. If you lived inside one of the galaxies, the night sky might change over immense timescales, but not in a single human lifetime, as a sudden catastrophe of stars falling everywhere. The danger to individual planets from direct stellar collision would be tiny, because stars are so widely separated. Yet the sky would eventually become more crowded and spectacular as the other galaxy approached, its stars spreading across the night like a second Milky Way. Over deep time, the structure of the whole galaxy would shift. Spiral arms could be stretched or destroyed. Gas could be consumed in bursts of star formation. Central black holes, if both galaxies have them, could sink toward the new center and eventually merge, releasing gravitational waves. The final result of a major merger is often an elliptical galaxy or a larger, more rounded system, depending on the masses, gas content, and details of the encounter. This is one way galaxies grow. They are not born once and left unchanged. They build themselves through smaller mergers, close encounters, accretion of gas, and long histories of gravitational interaction. The Milky Way itself carries evidence of past mergers. Streams of stars around our galaxy suggest that smaller galaxies have been pulled apart and absorbed over time. Even now, our galaxy is interacting with smaller companions, and in the far future, it is expected to merge with the Andromeda galaxy. That future merger will not mean the Sun is likely to crash into another star. By then, the Sun itself will be in a later stage of life, and Earth's future will depend more on the Sun than on direct galactic impact. But the merger will transform the architecture of our galactic neighborhood. Two great spiral galaxies will pass through each other, separate, fall back together, and eventually settle into a new combined system. The name often imagined for that future galaxy is Milky, though the real object will not care what we call it. What matters is that even our home galaxy is not exempt from cosmic change. It is part of a universe where structures meet, merge, and become something else. And this is the deeper lesson hidden inside galactic collisions. Emptiness does not mean nothing happens. The spaces between stars prevent constant direct impacts, but gravity fills those spaces with influence. A galaxy can pass through another galaxy without many stars hitting, and still both galaxies can be permanently changed. The invisible relationships matter more than the visible impacts. That is why this topic feels so different from ordinary violence. A car crash is defined by contact. A galactic collision is defined by fields, motion, tides, compression, and time. It is a collision where most objects miss, yet the whole system is transformed. It teaches you that scale changes the meaning of words. Collision at the human scale means broken surfaces. Collision at the galactic scale means reshaped destiny. The stars continue burning, often untouched as individual bodies, while the galaxy they belong to loses its old identity and becomes part of something larger. There is a quiet philosophical weight in that. You can survive an encounter and still be changed by it. You can pass through another system without direct impact and still have your path rewritten. Galaxies show that transformation does not always require physical contact at every point. Sometimes it is enough to come close enough for gravity to do its slow work. So when you imagine galaxies colliding, do not picture a simple explosion of stars smashing together. Picture a vast silent meeting of structures, where hundreds of billions of suns move through open space, where gas clouds compress into newborn stars, where long tails of starlight are pulled into the dark, where black holes may eventually spiral together, and where two ancient systems lose their separate shapes to become one new cosmic body. Galaxies collide without many stars hitting, and that is not a lesser kind of drama. It is a deeper one, a reminder that the universe can remake entire islands of light, not by crashing every piece together, but by changing the paths between them. Neutron stars can merge and forge heavy elements. The gold in a ring may have been born from one of the most violent collisions the universe can produce. Two dead stars spiraling into each other until space itself trembles. A neutron star is not an ordinary star still burning with gentle light. It is what can remain after a massive star's core collapses, leaving behind an object so dense that a spoonful of its material would have a mass beyond anything your senses can honestly imagine. It is not dense like metal, not dense like rock, not dense like the center of Earth, but dense in a way that pushes matter into an extreme state where atoms as you know them are crushed out of their familiar form. Protons and electrons are forced together, neutrons dominate, and the result is a stellar remnant only about the size of a city, but containing more mass than the Sun. Now imagine two of these objects orbiting each other. They may have once been a pair of massive stars, living together, dying separately, each leaving behind a neutron star. For a long time they can circle in darkness. Not peacefully exactly, but steadily, losing a little orbital energy as they send out gravitational waves, tiny ripples in space-time that carry energy away from the system. As that energy leaks outward, the two neutron stars draw closer. Their orbit tightens. They circle faster. The dance becomes more intense. What begins as a slow cosmic pairing turns, over immense time, into a final plunge. In the last moments, they whirl around each other hundreds of times per second, tearing at each other with gravity, distorting their shapes, heating matter to extraordinary temperatures, and then merging in a catastrophic event that can release more energy in a brief flash than the Sun will radiate across its entire lifetime. But the most astonishing part is not only the violence, it is the chemistry. Neutron star mergers are among the best-known natural sites for a process called rapid neutron capture, where atomic nuclei are flooded with neutrons so quickly that they can build into much heavier elements before they have time to decay. This is one of the main ways the universe can create many of the heaviest elements, including gold, platinum, and other rare materials that ordinary stars cannot easily make in large amounts. A normal star can fuse lighter elements in its core step by step while it lives. But to build the heaviest elements, nature needs extreme conditions: a storm of neutrons, heat, pressure, and explosive motion. In a neutron star merger, some neutron-rich material is thrown outward into space. That ejected matter is not just debris. It is a kind of cosmic furnace cooling in real time, where new heavy nuclei form and then decay into more stable elements. The light from this event is called a kilonova, a glow powered by the radioactive decay of freshly made heavy elements. Unlike a supernova, which comes from a star's explosive death, a kilonova comes from the merger of compact stellar remnants, and its color changes as the expanding material cools and as different elements affect how light escapes. In 2017, scientists observed an event that transformed this idea from theory into a new era of evidence. Gravitational wave detectors picked up the signal from two neutron stars merging, an event known as GDI 70817, and telescopes around the world then found light from the same cosmic collision in a distant galaxy. For the first time, astronomers could study both the ripples in space-time and the light from the same neutron-star merger. It was as if the universe sent the same story in two languages at once, one written in gravity, the other written in radiation. The observations matched the long-held idea that neutron star mergers can produce heavy elements through rapid neutron capture. Scientists saw signs of a kilonova and evidence that large amounts of heavy material had been created. This does not mean every atom of gold in the universe comes only from neutron star mergers, and it does not mean the full story of heavy element creation is completely finished. Some heavy elements may also be made in certain kinds of supernovae or other rare extreme environments. But neutron star mergers are now understood as a major source, and perhaps one of the most spectacular. That changes how you think about matter. Gold no longer feels like a quiet metal dug from the ground. Platinum no longer feels like a luxury material separate from the sky. These elements become survivors of catastrophe, ashes of dead stars that met again after death and turned their final collision into a factory for rarity. The jewelry on a human hand, the precious metal in electronics, the heavy atoms hidden in Earth's crust may carry an ancestry older and more violent than any civilization. Before they were mined, shaped, traded, or valued, they were forged in a place where two crushed stellar cores collided and sprayed neutron-rich matter into space. Later, that matter mixed into interstellar clouds. Later still, some of it became part of new stars, new planets, and eventually Earth itself. The story of heavy elements is not a simple line from star to planet. It is a cycle of death, mixing, rebirth, and assembly across billions of years. And this is where the science becomes quietly personal. You may think of the universe as distant, but some of its most extreme events have left traces inside the ordinary objects around you. A neutron star merger may happen far beyond human reach, in a galaxy you will never visit, and still its products can one day become part of a world like ours. The rare metal in a circuit, the dense element in a laboratory sample, the shimmer of gold under lamplight, these are not just materials. They are messages from violent cosmic ancestry. They remind you that the universe does not create complexity only through calm growth. Sometimes it creates through collision. Sometimes two remnants of dead stars meet. And instead of producing only destruction, they scatter ingredients for future worlds. That is the strange generosity of physics. What looks like an ending at one scale becomes a beginning at another. The merger may be brief, but its chemical consequences can last for billions of years. So when you hear that neutron stars can merge and forge heavy elements, do not imagine it as a distant trivia fact. Imagine two city-sized remnants heavier than suns, locked in a final spiral, shaking space-time, ejecting neutron-rich matter, and lighting the darkness with a kilonova glow. Imagine the atoms born there traveling through space, joining clouds, entering planets, waiting silently beneath rock until a mind on a small world learns to trace their history back to the collision that made them possible. And then let the thought settle softly. Some of the rarest beauty in your world was not made gently. It was forged when dead stars met again. And in their final violence, the universe learned how to make gold. Supernovae create and spread elements. A supernova is not only a star dying, it is the universe opening its furnace and throwing the ingredients of future worlds into space. For most of a star's life, its light can seem calm from far away, almost gentle, like a steady lamp burning in the dark. But inside a massive star, there is a long struggle between gravity pulling inward and heat pushing outward. The star survives because nuclear fusion in its core releases energy, and that energy helps resist collapse. At first, hydrogen fuses into helium. Later, in massive stars, heavier elements can be built in stages as the star ages and its core grows hotter. The inside becomes layered, almost like an onion made of fire. Different shells where different kinds of fusion occur, creating elements such as carbon, oxygen, neon, magnesium, silicon, sulfur, and others. But this process has a limit. Fusion can release useful energy up to the formation of iron group elements, and once the core becomes dominated by iron, the star enters a dangerous state. Iron does not give the star the same kind of energy support when fused under normal stellar conditions. The furnace reaches a wall. Gravity, patient for millions of years, suddenly wins. The core collapses in a fraction of a second, crushing inward with unbelievable force, while the outer layers of the star begin to fall after it. Then comes the explosion, a supernova, a catastrophic release of energy that can briefly outshine an entire galaxy. But the explosion is not just bright, it is chemically important. The intense heat, pressure, shock waves, and particle reactions inside the event create and rearrange elements, while the blast throws both newly made and previously formed material into surrounding space. This is how a star stops being only a star and becomes part of the raw material for whatever comes next. The oxygen you breathe, the silicon in rocks, the calcium in bones, the sulfur in minerals, and much of the iron in planets are connected to stellar generations that lived, transformed, and returned their material to space. Not every atom in your body was made in one supernova, and not every element comes from the same kind of stellar event. But supernovae are among the great distributors of the universe's chemical richness. Without them, many elements would remain locked inside stars, or never be created in the same abundance. A star could make oxygen deep inside itself, but if it never released that oxygen, it would not help build planets, atmospheres, oceans, or living bodies. The explosion matters because it spreads the ingredients outward. It is cosmic recycling on a scale so vast that death becomes delivery. There are different kinds of supernova, and they teach different chemical lessons. A core collapse supernova happens when a massive star's core gives way, leaving behind a neutron star or black hole while ejecting outer layers enriched by fusion and explosive processes. A type Ia supernova is different. It involves a white dwarf, the dense remnant of a smaller star, in a system where it gains material from a companion or merges with another white dwarf until a runaway thermonuclear explosion occurs. Type Ia supernovae are especially important sources of iron and nickel in the universe, and because they can reach a fairly predictable brightness, they have also helped astronomers measure cosmic distances. So supernovae are not all the same kind of death. Some are the collapse of a massive stellar core, others are the explosive destruction of a dense stellar remnant. But both can enrich space and change what future generations of stars and planets are made of. This is why astronomers study supernova remnants, the expanding clouds left behind after the blast. These remnants are not just beautiful shapes in telescope images, they are chemical maps. When scientists split their light into spectra, they can identify fingerprints of elements: oxygen, sulfur, silicon, iron, and more. The colors in many images may be assigned to different wavelengths, but the data behind them is real. It shows that the debris of a dead star is not empty smoke. It is structured material, heated gas, expanding shock fronts, magnetic fields, and atoms that will eventually mix into the interstellar medium. Over long timescales, that enriched material can become part of giant molecular clouds, the cold regions where new stars are born. Some of those new stars may form with planets. Some of those planets may contain rock, metal, water, and the chemistry needed for life. So a supernova is not the end of matter. It is a violent change in its address. What was once hidden inside a star becomes available to the galaxy. And there is another layer to the story. Supernova shockwaves can help compress nearby gas clouds, sometimes encouraging regions of star formation. The same blast that destroys one star may help trigger the birth of others. It can carve bubbles in space, push material outward, stir the gas between stars, and inject energy into the galaxy. In this way, supernovae act like engines of circulation. They prevent galaxies from being chemically still. They keep matter moving, mixing, heating, cooling, collapsing again. A galaxy without stellar death would be poorer, quieter, less able to build complex worlds. The early universe began mostly with hydrogen and helium, with only small traces of light elements. The rich periodic table you know did not appear all at once. It had to be made across cosmic history by stars, stellar winds, supernova, mergers, and other extreme events. Supernovae are one of the reasons the universe became chemically layered enough for planets like Earth to exist. They are part of the bridge between simple beginnings and complex reality. And perhaps the most haunting part is that the violence is not wasteful. A supernova looks like destruction because a star is torn apart. But from the wider view, it is also generosity. The star gives back. It releases what it spent its life making. It scatters atoms into the dark. And those atoms do not carry labels saying where they came from. They drift, mix, cool, and wait. Billions of years later, some may become a grain of dust, a planet's crust, a drop of blood, a breath, a thought. When you touch stone, when you see iron rust, when you feel the strength of your bones, you are touching the afterlife of stars. Not in a mystical way, but in a physical one. Your body is not separate from cosmic history. It is assembled from matter that has been processed, scattered, and gathered again. Supernovae create and spread elements, but they also change the meaning of endings. They show that nature can take collapse and turn it into distribution, take a star's final crisis and turn it into a galaxy's future inventory. So when you imagine a supernova, do not see only a flash in distant space. See a star reaching the last limit of its internal balance. See its core fail, its outer layers erupt, its elements thrown into the interstellar dark. See shockwaves carrying chemistry outward. See future clouds forming from enriched debris. See planets waiting in material that has not yet become planets. And then let the thought settle softly. The universe learned to build you not by avoiding destruction, but by using it. Somewhere long before Earth, stars had to die loudly enough for their hidden elements to become part of the world you now call home. The Milky Way will merge with Andromeda. The night sky already contains the outline of a future so enormous that no human civilization will be here to watch it unfold from beginning to end. Andromeda, the nearest large spiral galaxy to the Milky Way, is not just a faint smudge beyond the stars. It is another island of hundreds of billions of suns, a whole galactic city moving through the local group on a path that has long suggested an eventual meeting with our own. If you stand under a dark sky and find Andromeda with your eyes or binoculars, you are not looking at something safely frozen in the distance. You are looking at a neighboring galaxy whose motion is part of our galaxy's future. For decades, astronomers have expected the Milky Way and Andromeda to approach, interact, pass through one another, swing apart, fall back together, and eventually settle into one larger galaxy over billions of years. But the story is not as simple as a countdown clock. The two galaxies are separated by about 2.5 million light years, and Andromeda is moving toward us. Yet its sideways motion is extremely difficult to measure precisely. That sideways motion matters because a small difference in direction over millions of light years can decide whether two galaxies collide directly, graze one another, or delay their final merger far into the future. This is where the future becomes less like a prophecy and more like a calculation with uncertainty. Older models made the merger feel almost inevitable, often placing the first major encounter roughly 4 to 5 billion years from now. Newer work, using more refined measurements and including the gravitational influence of nearby galaxies such as the Triangulum Galaxy and the Large Magellanic Cloud, has made the picture more complicated. Some models suggest the merger may be much less certain within the next 10 billion years, while others still favor a high probability. So the honest version is this: the Milky Way and Andromeda are on a deeply connected future path. A merger remains a major and plausible outcome, but the exact timing and certainty are still being studied. That uncertainty does not make the story weaker, it makes it more real. The future of galaxies is not a myth written in advance. It is a gravitational negotiation among massive systems, hidden halos of dark matter, satellite galaxies, and motions measured across unimaginable distances. If the classic merger scenario unfolds, the first change would not be a sudden cosmic disaster. Andromeda would slowly grow larger in the night sky over millions and then billions of years, becoming not a faint patch, but a vast luminous structure stretching across the heavens. Long before the galaxies fully merged, their outer halos would begin to overlap. Invisible dark matter halos, far larger than the bright stellar disks, would interact gravitationally. The galaxies would tug at each other. Their disks would warp. Streams of stars could be pulled outward, and gas clouds could be disturbed. To any observer on a surviving world, the sky might become breathtakingly strange. Andromeda's spiral structure swelling larger, its core brightening in the distance, its companion galaxies drawn into the dance. Yet the event would unfold so slowly that no single lifetime would see it as a rapid crash. A human could be born, grow old, and die while the sky changed only subtly. Galactic time is not human time. It moves like geology multiplied by starlight. And perhaps the most surprising part is that the solar system would probably not be struck by another star. Stars are so widely separated that even in a merger of two huge galaxies, direct star-to-star collisions would remain extremely rare. The real transformation would be orbital. The Sun, or whatever remains of it by then, could be thrown into a different path around the new combined galaxy. Some simulations suggest our solar system might be pushed farther from the galactic center, perhaps into a more distant halo-like orbit. But by the time this galactic event becomes dramatic, the Sun itself will also have changed. In several billion years, the Sun will be brighter than it is now and eventually enter a red giant phase, creating serious problems for Earth long before the final galactic merger is complete. That means the Andromeda encounter is not the main near-term threat to life on Earth. The future of our planet is tied more closely to the aging Sun than to the meeting of galaxies. And still, the merger matters because it shows that even the galaxy we call home is temporary in its current form. The Milky Way feels permanent because it outlives us so completely. Its band of light has watched over every human story, every migration, every language, every fire, every city, every telescope. But the Milky Way is not a fixed object. It has consumed smaller galaxies before. It is absorbing streams of stars even now. Its shape, mass, and future are part of an ongoing history of growth and disturbance. Andromeda has its own merger history too. These galaxies are not pristine spirals untouched since birth. They are survivors of earlier encounters, carrying scars and streams, warped disks and satellite systems, histories written in the motion of stars. A future merger would be another chapter in that long evolution. If the two central supermassive black holes eventually sink toward the shared center of the new galaxy, they may orbit each other and merge as well, releasing gravitational waves across the universe. Gas compressed during the interaction could trigger new star formation in some regions, while other gas might be heated or stripped, changing how many new stars the merged galaxy can make. Over time, the elegant spiral patterns of the Milky Way and Andromeda could fade into a larger, rounder, more elliptical system. Some people call this imagined future galaxy Milkomeda, a playful name for something almost impossible to emotionally contain. Two great stellar homes losing their separate identities and becoming one. But this should not be imagined as a clean blending of paints. It would be a long rearrangement of orbits, a slow reorganization of stars, gas, dark matter, and remnants, with waves of structure forming and dissolving over immense stretches of time. What makes this future so haunting is that it forces you to see home as temporary at every scale. A house changes, a city changes, a planet changes, even a galaxy changes. The Milky Way, which feels like the backdrop of existence, is itself only a phase. Its spiral arms, its central bar, its satellite galaxies, its glowing river across Earth's night sky, all of this belongs to an era, not an eternity. Andromeda is not an enemy coming to destroy us. It is a partner in a future transformation neither galaxy chose, because galaxies do not choose. Gravity writes their long-distance relationship. Motion carries them forward. Mass bends their paths into consequence. If the merger happens, it will not be a sudden ending, but a vast becoming. A reminder that the universe builds through encounters as much as through isolation. And if newer measurements show that the exact outcome is less certain than once believed, that too teaches something valuable. Even on the scale of galaxies, the future is not always a single locked line. It is shaped by many bodies, many motions, and uncertainties so small in measurement that they become enormous over time. So when you look toward Andromeda, do not see only a distant galaxy. See a possible future written faintly in the sky. See another spiral system approaching across millions of light years. Not as a monster, not as a fireball, but as a gravitational companion whose fate is entangled with ours. See the Milky Way not as a permanent kingdom, but as a living structure in cosmic time, still changing, still responding, still unfinished. And let the thought settle gently. The galaxy that gave birth to the sun may one day lose its name, its shape, and its solitude, merging into something larger than itself. The stars will mostly miss each other, but the meaning of home will change completely. Black holes can evaporate. Theoretically. A black hole may look like the final prison of the universe, but physics quietly suggests that even this darkness might not last forever. For a long time, black holes were imagined as perfect endings, places where matter, light, information, and history crossed a boundary and never returned. They seemed like cosmic full stops, objects that could grow by swallowing material but could never truly shrink. Once something became a black hole, the story appeared finished from the outside. More mass could fall in, the event horizon could expand, but nothing could come back out. Then Stephen Hawking changed the emotional meaning of black holes by joining two ideas that do not sit easily together. Quantum physics, where empty space is never completely still, and general relativity, where gravity changes the structure of space-time. His conclusion was startling. Black holes may not be perfectly black. They may emit an extremely faint form of radiation, now called Hawking radiation, and by doing so, they may slowly lose energy. Since energy and mass are connected, a black hole that radiates can gradually lose mass. In the deepest future, if nothing keeps feeding it, it can theoretically shrink and eventually evaporate. This does not mean black holes are glowing like stars. It does not mean telescopes can easily watch a normal astrophysical black hole steam away. For black holes formed from collapsed stars, the effect is so incredibly weak that it is overwhelmed by the radiation around them in the present universe. A typical stellar mass black hole is far colder than the cosmic microwave background today, so it would actually absorb more energy from its surroundings than it loses through Hawking radiation. Only in a far future, when the universe has cooled enormously and the background radiation has faded, would such black holes begin to lose more than they gain. And even then, the timescales are almost beyond language. A black hole with the mass of the sun would take far longer than the current age of the universe to evaporate. Not by a little, but by an amount so vast that ordinary numbers stop feeling human. Supermassive black holes would last even longer, surviving through eras when stars have faded, galaxies have changed, and the universe has become colder and emptier than anything we can easily picture. So when you hear that black holes can evaporate, do not imagine a quick disappearance. Imagine the slowest possible kind of fading, a process so patient that the universe must grow ancient around it before it becomes important. The simple explanation often says that pairs of particles appear near the event horizon. One falls in and the other escapes, making the black hole lose energy. That picture can help the mind begin, but it is only a rough story, not the full physics. The deeper idea involves quantum fields in curved space-time, and how what one observer calls empty space may not look completely empty when an event horizon is present. The black hole's gravity and horizon change the way quantum fields behave, and to a distant observer, radiation appears to come from the black hole. The result is that a black hole has a temperature. This is a strange sentence because temperature usually belongs to ordinary things: air, water, skin, metal, fire. But Hawking's work suggested that black holes obey thermodynamic rules. They can have entropy, a measure connected to the number of hidden internal possibilities, and that entropy is related to the area of the event horizon. Suddenly, the event horizon was no longer just a boundary of no return. It became part of a deeper puzzle about heat, information, gravity, and quantum theory. This is why black hole evaporation is so important. It is not only a claim about black holes slowly shrinking, it is a clue that our understanding of reality is incomplete. If a black hole forms from matter carrying information, and then eventually evaporates into radiation that looks thermal and featureless, what happens to the information about what fell in? Is it destroyed? Is it somehow encoded in the radiation? Does it remain on the horizon in a way we do not yet understand? This is the black hole information paradox, one of the great unresolved questions in theoretical physics. It matters because quantum physics strongly suggests that information should not simply vanish from the universe, while black holes appear to hide information behind horizons. Hawking radiation turns that tension into a crisis. If the black hole never evaporated, the information could remain hidden forever. But if the black hole evaporates completely, the question becomes unavoidable. Where did the information go? Scientists have proposed many possibilities, involving holographic ideas, subtle correlations in radiation, quantum gravity, and new ways of thinking about space-time itself. There is no simple final answer yet, and that honesty should make the subject more fascinating, not less. Black hole evaporation is not a fully observed astrophysical process in the everyday sense. Hawking radiation from ordinary black holes is far too faint for current instruments to detect directly, but the theory connects so many deep principles that physicists take it seriously as a window into whatever future theory will unite gravity with quantum mechanics. It tells us that black holes are not merely objects in space. They are laboratories for the limits of knowledge. They ask what heat means when the object has no surface you can stand on. They ask what emptiness means near a horizon. They ask whether time, information, and gravity can be reconciled in one complete picture. And in the far future, if Hawking's prediction is correct, the final stages of a shrinking black hole would become more intense. As a black hole loses mass, it becomes hotter, and as it becomes hotter, it radiates faster. The ending would not be a slow fade forever, but a final acceleration, possibly ending in a burst of high-energy radiation for very small black holes. Some scientists have searched for signs of tiny primordial black holes evaporating, hypothetical black holes that might have formed in the early universe. But no confirmed detection has shown such an event. For the black holes we know from stars and galactic centers, evaporation remains a future too distant to witness. Still, the idea changes how you feel about darkness. A black hole is not simply an eternal mouth in the cosmos. It may be temporary on the longest scales nature allows. It may spend unimaginable ages holding its boundary, then slowly give its mass back to the universe as faint radiation, becoming smaller, hotter, and finally gone. The most permanent-looking object in existence may be another process, another phase, another form that time can eventually undo. And perhaps that is the quiet lesson hidden in Hawking radiation. Even the deepest darkness may have a temperature. Even the strongest boundary may leak in a subtle way. Even the places that seem to erase everything may still be part of a larger conservation of meaning we do not yet understand. So when you imagine a black hole evaporating, do not picture ordinary smoke rising from a dark sphere. Picture the meeting point of gravity and quantum uncertainty. A horizon whispering radiation across impossible ages. A cosmic object slowly paying back its mass to the universe. Black holes can evaporate theoretically, And whether or not humanity ever watches one complete that journey, the idea itself already does something powerful. It turns the symbol of finality into a question, and reminds you that in the universe, even endings may not be as absolute as they appear. Time near a black hole behaves strangely. Near a black hole, time does not simply pass. It bends into a different kind of experience, as if the universe has placed one clock beside a deep well and another far away in open space, then allowed both to tell the truth in different languages. This is one of the most unsettling consequences of Einstein's gravity. Time is not the same everywhere. It is not a single invisible river flowing at one universal speed for every planet, star, observer, and falling object. Time is affected by gravity, and the stronger the gravitational field, the more slowly time passes, compared with a region farther away. Around Earth, this effect is real but small. Around a black hole, it can become extreme. The closer you get to the event horizon, the more your clock appears to slow down from the viewpoint of someone watching safely far away. Not because your clock is broken, not because time is an illusion, but because time itself, as measured between different places in curved space-time, does not behave with the simple sameness your everyday life teaches you to expect. Imagine two astronauts. One remains far from the black hole, where gravity is weaker, while the other travels closer and closer toward the dark boundary. Each astronaut carries a perfect clock. To the traveler near the black hole, their own clock feels normal. Their heartbeat, thoughts, instruments, and breathing all continue in the ordinary rhythm of their local experience. They do not feel their personal seconds dragging like cold syrup. A second beside them still feels like a second. But when the distant astronaut compares signals from the traveler's clock, something strange appears. The closer the traveler gets to the event horizon, the slower those signals seem to arrive. Their light becomes stretched toward redder wavelengths. Their motions appear delayed. Their voice, if somehow transmitted outward, would become lower, slower, and fainter. From far away, the traveler seems to approach the horizon more and more slowly, as if the universe is reluctant to let the final moment become visible. In the mathematical description, the distant observer never quite sees the traveler cross the event horizon. The image becomes dimmer and more red-shifted until it effectively fades away. But from the traveler's own perspective, if they were falling freely and survived the tidal forces long enough, they could cross the event horizon in a finite amount of their own time. This is the strange double truth of black holes. What happens depends on where the clock is, who is measuring, and how the path through space-time is arranged. There is no need to say one observer is lying. Both are describing reality from different positions. This is why black holes are not only objects of darkness, but objects of disagreement between viewpoints. They reveal that time is personal in a physical sense, not emotional or imaginary, but measured by the path you take through gravity. The deeper you go into a gravitational well, the more your time separates from the time of someone far away. And this effect is not just theory. Gravitational time dilation has been tested in weaker forms around Earth and is part of the real physics of clocks and satellites. A black hole is where the same principle becomes almost mythical in scale. If you could hover near a black hole without being destroyed and without using impossible amounts of fuel, you might experience a short period while far away. Years or much longer pass elsewhere, depending on how close you are and what kind of black hole it is. This idea appears in science fiction because it feels like a doorway into time travel, but the real science is more careful. It does not let you travel backward into your own past. It does allow a form of one-way time travel into the future. Spend time in a region where your clock runs slower compared with distant clocks. Then return, and more time has passed for others than for you. Near a black hole, the difference could be enormous, but surviving the journey would be the challenge. Smaller black holes can create lethal tidal forces near the event horizon, stretching objects violently because gravity changes sharply over short distances. Supermassive black holes with much larger horizons can be gentler at the boundary itself, though getting close, hovering there, escaping, and dealing with radiation from nearby matter would remain a profound problem. Around an actively feeding black hole, the environment can be filled with intense heat, high-energy radiation, magnetic turbulence, and fast-moving gas. Time behaves strangely there, but space is not a calm laboratory waiting for visitors. It is an extreme environment where physics becomes both precise and unforgiving. The strangeness deepens when you consider light. Light climbing away from a black hole loses energy, becoming redder as it escapes the deep gravitational field. This gravitational redshift is not caused by the light getting tired in a vague way. It is a result of how energy and time relate in curved space-time. To a distant observer, processes near the black hole appear slowed, and the escaping light carries that slowdown in its stretched wavelength. This is one reason the region near a black hole can look visually distorted. Light paths bend, images can be warped. The far side of an accretion disk can appear lifted into view by gravity's bending of light. Some photons may orbit briefly near the black hole before escaping, creating rings and repeated images that carry information from regions where space-time is profoundly curved. Time and light become entangled in the geometry. A clock near the black hole, a photon leaving the disk, a distant telescope receiving that photon, all belong to one connected story about how gravity shapes measurement itself. There is also a point inside the black hole where the familiar meaning of direction changes in a way that is difficult to imagine. Outside the event horizon, you can choose different paths, at least in principle. Inside, all future-directed paths lead deeper inward. This does not mean time literally turns into space in a simple poetic way, but the roles of coordinates shift so severely that avoiding the central fate becomes as impossible as avoiding tomorrow. You can no longer choose a path that leads back out, just as you cannot choose to move into yesterday. That is one of the reasons black holes feel so philosophically powerful. They are not merely strong gravity. They are places where the structure of future possibility narrows. Outside, time dilation can let one observer see another slow toward the horizon. Inside, the future itself points inward. But it is important not to exaggerate beyond what science says. We do not yet have a complete theory that describes the deepest interior of a black hole, where general relativity predicts a singularity and quantum gravity is expected to matter. The singularity may signal that our current theory has reached its limit. Not that we fully understand a physical point of infinite density. What we can say with confidence is that near the event horizon, general relativity predicts extreme time dilation relative to distant observers, and observations around black holes support the broader framework. We see stars orbiting compact massive objects in ways that match relativity. We detect gravitational waves from black hole mergers, carrying information about spacetime under extreme conditions. We image glowing material around black holes, shaped by gravity and motion. None of this makes time near a black hole simple, but it makes the strangeness real rather than decorative. And perhaps this is the quiet lesson. Time is not the background of your life in the simple way it feels. You live in a mild gravitational environment, moving slowly compared with light, surrounded by clocks that mostly agree with one another, so time seems universal. But the universe has places where that agreement breaks. Near a black hole, seconds become local. Distance changes the rhythm of reality. A far observer, a falling traveler, a beam of light, and a clock near the horizon each reveal a different face of time, and none of them can be reduced to the simple ticking you feel in your room. So when you imagine time near a black hole, do not picture a magical stopwatch freezing for everyone. Picture a universe where gravity changes the relationship between clocks, where your own time can feel normal while someone far away watches your signals slow and redden, where the boundary of no return makes the future more restrictive than any wall. Time near a black hole behaves strangely because time is part of the fabric being curved. And in that strangeness, the universe whispers something both scientific and deeply humbling. The rhythm you trust is not the rhythm of all things. It is only the rhythm of where you are. Wormholes are mathematical possibilities, not proven roads. A wormhole is the kind of doorway the equations can draw, but the universe has never promised to build. It is one of the most tempting ideas in all of physics. A tunnel through space-time, a hidden passage connecting two distant regions, a route that could make the unimaginable feel suddenly near. In movies, a wormhole is often shown as a glowing hole in space, a cosmic shortcut, waiting for a brave traveler to enter one side and emerge near another star, another galaxy, maybe even another time. But the real science is quieter, more careful, and in many ways more fascinating. Wormholes are not proven roads through the universe. They are mathematical possibilities that appear in certain solutions of Einstein's theory of gravity. And a mathematical possibility is not the same thing as a physical object waiting somewhere in the dark. This distinction matters deeply. Physics often begins with equations that allow strange shapes, strange motions, strange possibilities, but nature decides which of those possibilities actually exist. A map can contain a bridge drawn in ink, but that does not mean the bridge has been built across the river. Wormholes sit in that strange space between imagination and evidence. They are not pure fantasy, because they emerge from serious attempts to understand space-time, but they are not confirmed reality, because no telescope, detector, spacecraft, or observation has ever shown us a real traversable wormhole. The earliest famous version, the Einstein-Rosen bridge, came from mathematical work connected to black holes and general relativity. It suggested that space-time could, in principle, contain a bridge-like structure between two regions. But this was not the stable science fiction doorway people often imagine. In its standard form, it would not stay open long enough for a traveler to pass through, and it was not designed as a usable tunnel across the cosmos. Later, physicists explored whether a traversable wormhole could exist, one that remains open, does not collapse instantly, and allows something to pass through safely. That is where the problem becomes severe. To hold a wormhole throat open, many models require exotic matter, a kind of matter or energy with unusual properties, such as negative energy density. In simple terms, ordinary matter tends to pull inward through gravity. A traversable wormhole would need something that resists collapse in a very special way, something that can keep the passage open instead of letting gravity pinch it shut. We do see small quantum effects where negative energy-like behavior can appear in limited contexts, but nothing like the stable, large-scale material needed to hold open a human-sized cosmic tunnel has ever been found. So the dream remains suspended, possible in equations under certain conditions, unproven in the physical universe, and perhaps impossible in any practical sense. This is why wormholes are so often misunderstood. People hear aloud by Einstein's equations and quietly translate it into probably out there. But equations can allow many things that may never form naturally. A solution can be mathematically valid and still physically unrealistic, unstable, or dependent on ingredients the universe does not provide. Nature is not required to realize every permitted geometry. It is more selective than imagination. And even if wormholes do exist somewhere, they might be microscopic, temporary, hidden behind horizons, or completely non-traversable. They might be less like highways and more like mathematical hints about how space-time, gravity, and quantum information fit together. In modern physics, some of the most interesting wormhole discussions are not about travel at all. They are about deep connections between gravity and quantum theory, especially the idea that space-time itself may be related to entanglement. Some theories suggest that bridge-like structures could be connected to the way quantum systems share information. But this does not mean entangled particles are tiny usable tunnels or that humans can step through quantum links. It means wormholes may be clues, metaphors with mathematical teeth, pointing toward a deeper theory where geometry and information are not separate. That is already astonishing without turning it into a fantasy portal. The danger of exaggerating wormholes is that it makes the real mystery feel smaller. The truth is more subtle. Wormholes reveal that space-time may be far more flexible than everyday experience suggests. You live as if distance is absolute. A place is far because space lies between you and it. But general relativity taught us that space-time is not a rigid box. It can curve, bend, stretch, and change its shape under the influence of matter and energy. A wormhole is an extreme extension of that idea, not simply bending a path, but connecting regions in a way that could make two distant places neighbors through a different geometry. Imagine 2 points on a sheet of paper. If you travel along the paper, they may be far apart. But if the sheet could fold so the points touched, the distance through the fold could be much shorter than the distance across the surface. This analogy is common because it gives the mind a handle, but it is also incomplete. The universe is not literally a paper sheet folding through a higher room you can point to. The real mathematics involves space-time itself, not a simple surface in everyday space. Still, the analogy helps you feel why wormholes are so powerful as an idea. They challenge the assumption that the shortest path must look short from the outside. Yet every step from idea to reality becomes difficult. How would a wormhole form? Would it require conditions from the early universe? Could it survive cosmic evolution? Would it collapse before anything entered? Would radiation, quantum effects, or ordinary matter destabilize it? Would passing through it create paradoxes, especially if time differences between the two mouths allowed signals to return before they were sent? These are not small technical details. They are the reasons wormholes remain speculative. A real traversable wormhole would not only be a tunnel, it would be a test of causality, energy, gravity, and quantum theory at once. It would force physics to answer questions it has not yet fully solved. Could the universe allow shortcuts without allowing contradictions? Could space-time connect distant regions without breaking the order of cause and effect? Could a structure that looks possible on paper remain stable in the restless reality of quantum fields? No one knows, and that uncertainty should not disappoint you. It should sharpen the wonder. The most honest scientific ideas are not always the ones that promise easy travel. Sometimes, their power comes from showing the boundary between what we can imagine, what mathematics can describe, and what evidence can confirm. Wormholes stand exactly on that boundary. They ask you to respect the difference between a beautiful possibility and a proven road. They invite you to dream, but they also require humility. We have observed black holes. We have detected gravitational waves. We have mapped galaxies and measured the ancient glow of the early universe. But we have not found a wormhole. No confirmed lensing pattern, no strange repeated image, no signal in the sky has forced scientists to say, there it is. Until that happens, wormholes remain theoretical structures, useful for probing the limits of gravity, not established tunnels for cosmic travel. And perhaps that is what makes them emotionally powerful. A wormhole is a symbol of the human wish to make distance surrender. We want the universe to have hidden doors because the visible roads are too long. We want the stars to be reachable, the past to be negotiable, separation to be less final than it feels. But science at its best does not give comfort cheaply. It says, maybe space-time allows stranger connections than you think, but do not confuse the maybe with the known. Do not turn the mathematics into a doorway before the universe opens it. So when you imagine a wormhole, do not picture a guaranteed portal waiting between the stars. Picture a question carved into the structure of space-time. Picture equations bending into a bridge, then nature asking whether such a bridge can stand. Picture the difference between possibility and proof, between a road drawn in theory and a road walked in reality. Wormholes are mathematical possibilities, not proven roads, and that makes them more than a science fiction device. They are a reminder that the universe is not limited by our ordinary intuition, but our beliefs must still be limited by evidence. Somewhere between imagination and observation, the idea remains suspended, not closed, not confirmed, but quietly waiting at the edge of what physics can honestly say. The universe has no known edge. If you traveled in one direction for longer than any human mind can truly imagine, the strangest discovery might not be an edge, but the absence of one. The word universe makes us picture something with an outline, because almost everything we know has a boundary. A room has walls, an island has a shore, a planet has a surface, a body has skin. Your mind is trained by objects, and objects end. So when you hear the universe, a quiet part of you may imagine a gigantic container, a final shell, some distant place where the stars stop, and beyond it, there is either empty blackness or nothing at all. But modern cosmology gives a more careful and more unsettling answer. The universe has no known edge. Not no edge because we have already proven it goes on forever, and not no edge because we can see all the way across it. But no known edge because every serious observation so far shows no sign of a physical boundary where space ends. The edge people often imagine is usually a confusion between two very different ideas: the limit of what we can observe and the limit of what exists. We do have a horizon, a farthest region whose light has reached us, but a horizon is not a wall. It is a limit of information from our point of view. If you stand in fog and see only the nearby trees, the last tree you can see is not the end of the forest. In the same way, the farthest light we receive is not proof that space stops there. It is simply the farthest light that has had the right history to arrive. Beyond it, there may be more universe, perhaps much more, perhaps arranged in ways we cannot directly measure. The honest phrase is not, "We found the edge," but "We have not found one." And that difference matters, because science is not just about what sounds dramatic. It is about what evidence can support. When astronomers study the universe on the largest scales, they find that it looks broadly similar in all directions, once you average over the smaller details of galaxies, clusters, and voids. This large-scale sameness is one of the reasons the idea of a nearby cosmic boundary is hard to take seriously. If there were a physical edge not terribly far beyond what we can see, we might expect to notice some sign of it, a preferred direction, a sharp change, a distortion in the patterns of distant light, some clue that space behaves differently as we approach the supposed border. We do not see such a simple edge. Instead, the universe appears to extend beyond our visible reach without showing us a final rim. But this does not mean scientists simply declare infinity and walk away. There are several possibilities. The universe could be infinite, stretching endlessly in all directions, or it could be finite but unbounded, meaning it has a limited overall size while still having no edge you could reach. That sounds impossible only because we try to picture it from the outside. Think of the surface of Earth, not as a perfect explanation, but as a helpful hint. You can travel east around Earth and never reach an edge of the surface, even though the surface has a finite area. There is no place where the ground suddenly ends and says, "This is the border of Earth's surface." You can keep going and eventually return to where you began. The universe may not work like a simple two-dimensional surface, and we do not know its full shape. But the example shows something important. Having no edge does not automatically mean being infinite. A space can be finite and still not have a boundary. The full geometry of the universe could be more subtle than everyday imagination can draw. Scientists study this by looking at curvature, patterns in the cosmic microwave background, the distribution of galaxies, and whether light might reveal repeating structures across the sky. So far, the observable universe looks very close to flat on large scales, which is consistent with an infinite universe, but also consistent with a finite universe so large that our visible region is only a tiny patch too small to reveal the overall shape. Standing in a small field on Earth, the ground can look flat even though the planet is round. In a similar way, our observable region could look flat even if the total universe has a larger curvature or topology beyond our reach. This is why the phrase "no known edge" is more precise than "the universe definitely has no edge." We have not detected a boundary. We have not proven the whole shape. We live inside the evidence available to us, and the evidence says the cosmos is larger than our direct view and not bordered by any known physical rim. Another question often follows. If the universe has no edge, what is it expanding into? This question feels natural, but it may be built from the wrong picture. Expansion does not require the universe to be pushing into an outside emptiness like smoke filling a room. Space can expand by increasing the distances between faraway regions within itself. The universe is not necessarily an object sitting inside a larger container. There may be no outside in the ordinary sense. Outside the universe may be a phrase that sounds meaningful because language lets us say it, while physics may not give it a place to point. This does not mean we know there is absolutely no larger reality, no multiverse, no deeper structure, no unknown framework. It means our current observable universe does not present us with an edge or an external wall that science can identify. The mystery remains open, but it must be kept honest. We should not fill the unknown with fake certainty just because the mind dislikes blank spaces. And there is a deep emotional shift in accepting an edgeless universe. An edge would be comforting in a strange way. It would give the cosmos a shape like a room. It would let your imagination walk to the final border, place a hand on the last wall and say, "Here is where everything stops." But an edgeless universe removes that comfort. It says reality may not have the kind of ending your body expects. It may not be structured like a box, a building, a country, or a map with a neat line around it. The cosmos may be something you are inside without any outside boundary you can picture. It may continue beyond view, curve back in ways you cannot sense, or extend so far that the difference between very large and endless becomes unreachable to observation. And yet this does not make you lost. It makes your location more meaningful, not less. You are not standing near the edge of a cosmic container. You are standing inside a region of reality where matter gathered, stars formed, a planet cooled, life emerged, and consciousness learned to ask whether space itself has a border. That question is already astonishing. The universe does not need an edge to be real. It does not need a wall to have structure. It does not need a final boundary to contain histories, galaxies, laws, and possibilities. In fact, the absence of a known edge may be one of the clearest ways the universe teaches humility. It reminds you that human intuition evolved for hills, rivers, caves, shelters, and horizons, not for the total shape of space-time. Your imagination asks for a rim because your hands know cups and bowls, but the universe may not be the kind of thing a hand-shaped mind can enclose. So when you hear that the universe has no known edge, do not imagine empty words or vague mystery. Imagine a cosmos whose visible limit is not a border, whose full extent remains unmeasured, whose shape may be infinite, finite without boundary, or larger than any test we can perform from our small region. Imagine traveling farther and farther, not toward a final cliff, but into more space, more structure, more unanswered distance, and let the thought settle softly. Perhaps the universe is not something that ends the way objects end. Perhaps it is something that surrounds every question with a larger question. There is no known edge, and maybe that is why looking outward feels less like approaching a wall and more like awakening inside a mystery too vast to close. The shape of space could be flat or curved. The universe may have a shape that no eye can see from the outside, because there may be no outside place from which to look. When you picture shape, you usually picture the outline of something, the curve of a cup, the edge of a stone, the surface of a planet, the walls of a room. Shape in ordinary life belongs to objects sitting inside space. But when cosmologists ask about the shape of space itself, they are asking something far deeper and stranger. They are not asking whether the universe looks like a ball, a box, or a glowing cloud from far away, as if some observer could stand beyond everything and take a photograph. They are asking how space behaves from within. If you travel in straight lines, do those lines stay forever apart, slowly come together, or spread away from each other? If you draw an enormous triangle across the cosmos, would its angles add up the way they do on a flat sheet of paper? Or would the total be slightly different because space itself is curved? If light travels across vast distances, does it move through a geometry that is flat, positively curved, or negatively curved? These questions sound abstract, but they are not empty philosophy. The shape of space affects how light travels, how patterns from the early universe appear to us, and what the largest possible structure of reality might be. A flat space, in the cosmological sense, is not flat like a table because the universe is not a two-dimensional surface. It means that on the larger scales, geometry behaves in the familiar way. Parallel paths remain parallel, huge triangles follow the ordinary rules, and space has no overall curvature that we can detect. A positively curved space would be more like the surface of a sphere in spirit, though with more dimensions than the analogy can show. On Earth's surface, if you begin at the equator, travel north, then turn and travel along another great path, lines that began as separate can eventually meet. Triangles drawn on a sphere can have angles adding to more than you expect from flat paper. A negatively curved space is harder to picture, often compared to a saddle shape, where paths can diverge more strongly, and triangles can have angles adding to less. These analogies are imperfect because they use two-dimensional surfaces to help you imagine three-dimensional space, but they give the mind a first doorway. Curvature does not require space to bend into a visible higher room that you could point at. It means the internal rules of distance and direction are different. You can discover curvature by moving within the space and measuring it, not by standing outside it. This is why the universe's shape can be studied scientifically, even if we cannot escape it. One of the main tools is the cosmic microwave background, the ancient afterglow from the early universe. That light carries patterns from a time when the cosmos was much younger, and those patterns have a characteristic size. By comparing the apparent size of those patterns in the sky with what physics predicts, scientists can infer whether space is curved. If the universe were strongly positively curved, those patterns would appear magnified in a certain way. If it were strongly negatively curved, they would appear shifted differently. Observations so far show that the observable universe is very close to flat. That is a careful statement. It does not mean we know space is perfectly flat everywhere and forever. It means that within the part of the universe we can measure, any curvature is so small that space behaves almost exactly like flat geometry on the largest observable scales. This is one of the most astonishing results in cosmology, because there is no obvious everyday reason the universe had to be so close to flat. The balance between matter, energy, expansion, and geometry appears extremely precise. In cosmology, the overall curvature is tied to the total contents of the universe: ordinary matter, dark matter, radiation, dark energy, and whatever else contributes to the cosmic energy budget. Too much total density compared with a critical value, and space tends toward positive curvature in simple models. Too little, and it tends toward negative curvature. Very close to that critical balance, space appears flat. Current measurements suggest the universe is extremely close to that balanced case. But again, flat does not automatically answer every question. A flat universe could be infinite, extending without end, but a flat universe could also be finite in some more complicated topology. Like a video game space where traveling far enough in one direction could, in principle, bring you back from the opposite side. Though we have not found evidence that our universe works that way. Curvature and topology are related but not identical. Curvature tells you how geometry behaves locally and globally in terms of bending. Topology tells you how space is connected overall. A place can be flat and still have surprising connectivity. That is one reason the shape of space remains such a subtle subject. The universe can hide its full structure from observers trapped inside a limited region. If the total universe is much larger than what we can see, our observable patch may look flat even if the whole thing has a slight curve, just as a tiny patch of Earth's surface looks flat when you stand on it. This means the absence of detected curvature is powerful evidence, but not the same as seeing the whole. Science must keep both confidence and humility in the same hand. We can say the observable universe is very close to flat. We cannot honestly claim that we have stepped outside the cosmos and measured its complete form. The idea becomes even more meaningful when you realize that the shape of space is not a decorative detail. It is connected to the history and fate of the universe. Curvature influences how cosmic expansion behaves, how light from distant objects is interpreted, and how the largest scales of reality are modeled. In older simplified pictures, people sometimes linked a closed curved universe with eventual collapse and an open universe with endless expansion. But modern cosmology is more complicated because dark energy changes the story. A universe can be flat and still expand forever. A curved universe can have a fate shaped by more than curvature alone. The contents of space matter, not just its geometry. Still, geometry remains one of the deepest fingerprints of the universe's origin. Inflation, the idea that the very early universe may have expanded extremely rapidly for a brief period, helps explain why space appears so flat today. Rapid expansion could stretch any initial curvature until our observable region became like a tiny flat-looking patch of a much larger surface. This is not just a convenient image. It is one reason inflation became such an important idea, though the details of inflation are still studied and debated. The flatness of space is therefore not boring. It is a clue. It may be telling us that the early universe underwent a process that smoothed and stretched geometry far beyond our direct view, or it may be pointing towards some deeper principle we have not yet understood. Either way, the result is quietly strange. You live in a universe whose largest measurable geometry is almost perfectly balanced between curving one way and curving another. The ground beneath you feels curved because Earth is a sphere, but the space through which galaxies are spread appears within our measurements remarkably close to flat. And yet, that flatness is not something you can see by staring into the sky. It is something revealed through patterns, measurements, and the ancient light of the cosmos. Your senses are not built to detect the curvature of the universe. They are built for rooms, roads, bodies, and horizons. Cosmology asks them to step aside and let instruments extend perception into scales where intuition becomes unreliable. There is something deeply humbling in that. Space, the thing that seems most empty and obvious, may carry a geometry subtle enough that only the oldest light can help reveal it. The distance between galaxies is not only distance, it is part of a larger geometric question. Light traveling across the cosmos is not only a messenger of stars, it is a probe of the shape of reality. And if the universe is curved, it may be curved so gently that our entire observable world is too small to notice the bend directly. If it is flat, that flatness may itself be the result of a profound early process. Either way, the lesson is the same. The universe is not required to fit the shapes your imagination learned from objects. Its shape may be an internal rule, a hidden grammar of paths and distances, rather than an outline drawn against a background. So when you hear that space could be flat or curved, do not picture a simple diagram and think the mystery is solved. Picture yourself inside a geometry you cannot leave, measuring its nature by the behavior of light, ancient patterns, and enormous triangles written across the sky. Picture space not as emptiness, but as something with structure, balance, and history, and let the thoughts settle gently. The universe may have no visible wall, no outside viewpoint, no edge you can touch, yet it may still have a shape. Not the shape of an object, but the shape of possibility itself, guiding every beam of light and every distant galaxy through the quiet architecture of space. Cosmic inflation may explain large-scale smoothness. The universe looks too smooth for its own history, and that quiet smoothness is one of the reasons scientists began to suspect that something enormous happened almost before time had learned how to breathe. When we look at the cosmos on the largest scales, we do not see one side blazing wildly hotter than another, or one direction packed with matter, while another is almost completely different. We see a universe that once averaged over huge distances appears remarkably even. The ancient light of the cosmic microwave background arrives from every direction, with nearly the same temperature, differing only by tiny amounts, so small that they look like delicate fingerprints rather than violent scars. This is beautiful, but it is also a problem. In the simplest early universe picture, regions now on opposite sides of the sky seem too far apart to have exchanged light or heat with each other before the cosmic microwave background was released. If they had never been in contact, why do they look so similar? How did distant regions of the young universe agree so closely on temperature, density, and overall behavior? In everyday life, smoothness usually has a cause. A hot drink becomes evenly warm because heat spreads through it. A room reaches a shared temperature because air circulates. A rough surface becomes smooth because something rubs it down. But in the early universe, the large-scale agreement seems to appear across regions that should not have had enough time to communicate in the ordinary way. This is called the horizon problem, and it is one of the great clues that our first simple picture was missing something. Cosmic inflation was proposed as a way to solve this mystery. The idea is that extremely early in the universe's history, perhaps in a tiny fraction of its first second, space underwent a burst of extraordinarily rapid expansion. This was not ordinary expansion slowly carrying galaxies apart, because galaxies did not yet exist. It was a brief, powerful stretching of space itself, so extreme that a region that had once been small enough to be in contact could be blown up to a size far larger than the observable universe. In that picture, the reason distant regions of the sky look so similar is that they were once close enough to share conditions before inflation stretched them apart. They are like pieces of the same cloth pulled so far away from one another that they now seem unrelated, even though they began as part of one connected patch. This does not mean scientists have watched inflation happen directly. We cannot point a telescope at the first instant and see a movie of space swelling. Inflation is a theory, a powerful framework, supported by several important successes, but still under investigation. Its strength is that it explains multiple strange features at once. It helps explain the large-scale smoothness of the universe. It helps explain why space appears so close to flat across the observable region, because rapid expansion could stretch curvature until our patch looks nearly level, much as a tiny piece of an enormous balloon can look flat when viewed up close. It also provides a natural way to turn tiny quantum fluctuations into the seeds of later cosmic structure, because small early variations could be stretched to astronomical scales and later amplified by gravity. That combination is why inflation remains so influential. It does not solve only one puzzle, but connects several puzzles into one early cosmic event. Yet honesty matters. There are many models of inflation, and scientists still debate what physical field caused it, exactly how it began, how it ended, and whether it is the only possible explanation. Some alternatives try to explain smoothness and structure without inflation, and future observations may support, refine, or challenge parts of the inflationary picture. The best scientific attitude is not to turn inflation into a myth of certainty, but to treat it as a deeply successful and still unfinished idea. It is a bridge between what we can measure and what we are trying to understand. One of the most important pieces of evidence comes from the cosmic microwave background. This ancient radiation is often described as the afterglow of the early universe, but that simple phrase hides its richness. It is a map of the universe when it first became transparent, carrying tiny temperature variations that show where matter was slightly denser or slightly thinner. These variations are incredibly small, yet they are arranged in a pattern that fits the broad predictions of inflation very well. The universe is smooth, but not perfectly smooth. That balance is crucial. Inflation does not erase all structure. Instead, it can stretch tiny initial fluctuations into a nearly scale-balanced pattern, leaving the faint seeds from which galaxies and clusters eventually form. If the universe had been perfectly uniform, there would be no galaxies. If it had been wildly uneven, the cosmos might have become too chaotic for the structures we see. Inflation offers a way for the universe to begin with both order and possibility, smooth enough to be coherent, imperfect enough to grow. And this is where the idea becomes almost meditative. The universe did not become rich by beginning in loud complexity. It may have begun with a kind of hidden simplicity, then undergone a breathtaking expansion that smoothed the large-scale stage while preserving the tiniest variations as future instructions. Inflation turns the early universe into a moment of stretching so vast that ordinary words fail. Distances that were once microscopic could become cosmic. Curvature could be flattened. Local agreement could be spread across the sky. A small patch could become everything we can observe. And after that brief expansion ended, the universe continued its slower evolution. cooling, forming particles, atoms, stars, galaxies, planets, and eventually minds capable of asking why the cosmos looks so strangely uniform. But the most important thing is not to imagine inflation as an explosion into empty space. It is better to imagine space itself rapidly changing scale, expanding so quickly that the geometry and contents of the young universe were transformed before ordinary cosmic history unfolded. Inflation is not a fireworks show. It is more like a hidden preparation of the stage before the first lights of structure appeared. The audience arrives billions of years later, sees the stage astonishingly smooth, and asks why the floor is so even, why the backdrop matches in every direction, why the faint patterns are distributed with such delicate precision. Inflation answers, because the visible stage may once have been a tiny connected region stretched beyond recognition. That answer is powerful, but it also opens deeper questions. What powered inflation? Was it a special field with energy that briefly dominated the universe? Did inflation happen only once, or could it create regions beyond our observable patch? Did it leave behind subtle gravitational waves or polarization patterns in the cosmic microwave background that future instruments may detect? These questions are not failures. They are the living edge of cosmology. A good theory does not end curiosity. It organizes curiosity into sharper questions. Inflation makes predictions, and scientists continue testing them with CMB measurements, galaxy surveys, and searches for faint primordial signals. Some signals have not yet been found, and that absence also teaches us by ruling out certain versions of the theory. The story is still unfolding, and perhaps that is the soft lesson hidden in cosmic inflation. The universe's calmness may not be simple calmness. It may be the result of an ancient, almost unimaginable stretching that made the cosmos look smooth, while secretly preserving the small differences needed for everything later to form. The sky's uniformity is not emptiness. It is evidence. The tiny variations are not flaws. They are beginnings. So when you hear that cosmic inflation may explain large-scale smoothness, do not picture a final answer sealed forever. Picture an early universe with a mystery in its balance, too even to be accidental in the simplest picture, too delicately uneven to be lifeless. Picture a brief expansion so powerful that it could turn a small connected region into the vast observable cosmos, smoothing the whole while leaving faint seeds behind. And then let the thought settle gently. The universe may look calm on the larger scales, not because nothing happened, but because something unbelievably dramatic happened so early that only its quiet fingerprints remain. The vacuum has energy problems we don't fully understand. Empty space may be carrying a number so wrong in our theories that it has become one of the deepest embarrassments in physics. At first, vacuum sounds like nothing. No air, no dust, no sound, no particles drifting through a room, no obvious substance waiting to be touched. In everyday language, a vacuum is absence. It is what remains when everything else has been removed. But in modern physics, emptiness is not that simple. Even when you remove matter, even when you cool a region, even when no ordinary particle is sitting there like a tiny marble, the fields of nature still remain. The electron field remains. The electromagnetic field remains. Other quantum fields remain. And quantum fields do not behave like perfectly silent furniture. They have a lowest possible state. But that lowest state is not always the same as absolute zero activity. It can contain a kind of restless baseline, not a swarm of visible sparks, not little particles popping in and out like cartoon bubbles, but a deeper quantum uncertainty built into the way fields exist. This is where the idea of vacuum energy begins. The vacuum may not be true nothing, but a physical state with properties. And that sounds beautiful until gravity enters the room. In ordinary quantum physics, energy can often be shifted or redefined without causing obvious disaster. But in gravity, energy matters because energy affects the shape and expansion of space-time. If the vacuum has energy, even a uniform energy spread through empty space should influence the universe on the largest scales. It should behave something like a cosmological constant, a background contribution that does not clump into stars or planets, but still helps determine how space expands. And here the problem opens like a crack in the foundation. When physicists try to estimate the energy of the quantum vacuum in simple, naive ways, the result can be enormously larger than the tiny value implied by the observed acceleration of the universe. Not just a little too large, not a normal scientific disagreement that can be patched with a small correction. The mismatch is often described as one of the worst gaps between theoretical expectation and observation in all of physics. The universe seems to be saying, empty space has a small but important effect, while our theories, handled too directly, seem to shout back, it should be unimaginably larger. If that larger value were real in the simple way the calculation suggests, the universe would not look like the one we live in. Space would expand or curve in a wildly different way. Galaxies, stars, and planets might never have formed as we know them. Your existence depends quietly on this vacuum problem being somehow resolved by physics we do not yet fully understand. This is not just a mystery about darkness between galaxies. It is a mystery about the rules underneath reality. Why does empty space gravitate so gently? Why does the vacuum not tear the cosmos apart with the enormous energy our roughest calculations seem to imply? Is there a cancellation between different contributions so precise that almost everything subtracts away? Is there a hidden symmetry of nature that makes the vacuum energy small? Is our understanding of quantum fields in curved space-time incomplete? Is dark energy truly vacuum energy, or is it something that only looks similar from our current measurements? These questions are not decorations around the main story. They are the main story. The vacuum energy problem sits at the intersection of two great pillars of modern science. Quantum theory, which describes fields and particles with extraordinary success, and general relativity, which describes gravity, space-time, and cosmic expansion. Each pillar works beautifully in its own domain, but when they are forced to speak about the vacuum of the whole universe, they do not yet agree in a clean, finished way. It is like having two master maps of reality that both guide you perfectly through different landscapes. But when you lay them over the same empty region, the roads refuse to align. This is why the vacuum feels so strange. It is not empty enough to ignore, but not understood enough to explain. It has measurable consequences in some contexts, but its absolute gravitational meaning remains unresolved. For example, there are quantum effects such as the Casimir effect, where two closely placed conducting plates experience a tiny force related to changes in allowed quantum field modes between them. This shows that the quantum vacuum is not just philosophical emptiness. It can participate in real physical phenomena, but that does not automatically solve the cosmological problem, because measuring differences in vacuum energy in a laboratory is not the same as knowing the absolute vacuum energy that should gravitate across the universe. Gravity seems to care about total energy in a way that other forces often do not, and that is precisely where the difficulty becomes sharp. In particle physics, physicists can often use a process called renormalization to handle infinities and focus on measurable quantities. It is a powerful and successful method, not a trick. But when the vacuum energy is placed into cosmology, the question becomes more stubborn. What value should appear in Einstein's equations as the energy of empty space? Why is the observed value so tiny compared with many theoretical expectations? Why is it not exactly zero if some unknown principle cancels it? And why is it becoming important in the universe's history around the era when galaxies, stars, and observers like us exist? That last question is sometimes called the coincidence problem. Matter becomes diluted as the universe expands, while a constant vacuum energy would remain steady per volume. So why do we happen to live during a time when matter and dark energy are even remotely comparable in cosmic influence? Maybe it is coincidence. Maybe it points to deeper physics. Maybe it is connected to the fact that observers can only arise in universes or eras where structure has had time to form. But none of these possibilities is a simple final answer. They are paths into uncertainty. Some ideas suggest dark energy might not be a true constant, but a slowly changing field. Some suggest vacuum energy may evolve mildly with cosmic expansion. Some explore deeper quantum gravity, string theory landscapes, holographic ideas, or modifications to gravity itself. Each attempt tries to make sense of why empty space has the effect it does without ruining the universe we observe. But so far, there is no universally accepted solution. That is what makes this problem so powerful for a listener to feel. We are not talking about a small missing detail at the edge of science. We are talking about the meaning of emptiness. The vacuum is supposed to be the simplest state, the background after everything else is removed. Yet it may be hiding one of the hardest questions in physics. The word nothing begins to lose its innocence. Empty space may not be an absence, but a balance, a tension, a quiet state held between enormous theoretical contributions and a tiny observed cosmic effect. It may be that our concept of vacuum is still too tied to human intuition, too shaped by rooms and containers and the idea of removal. Nature's vacuum is not the emptiness of a cleaned box. It is the lowest state of fields, the background on which particles appear, forces act, and space-time responds. And if the vacuum has energy, then the background is not passive. It participates in the fate of the cosmos. It may be connected to the acceleration of expansion. It may decide how the largest distances change with time. It may help determine whether the universe fades into cold separation, changes into something stranger, or reveals some hidden layer of physics we have not yet named. But because we do not fully understand it, the vacuum also becomes a lesson in scientific humility. The most ordinary-looking thing, empty space, may be where our best theories show their deepest disagreement. You can look between stars and think you are seeing nothing, but physics tells you that nothing is a question mark with structure. It may contain fields, fluctuations, possible energy, and unresolved gravitational meaning. It may look silent because your senses were never built to hear what emptiness is doing. And perhaps that is the quiet, emotional force of this topic. The universe does not hide its hardest mysteries only in black holes or at the first moment of time. Sometimes it hides them in the spaces between things, in the background you ignore because it seems too empty to matter. The vacuum has energy problems we do not fully understand, and that sentence is not a weakness of science. It is a doorway. It means the story is still alive. It means the simplest word in the world, nothing, may be one of the most complicated. So the next time you imagine the emptiness between galaxies, do not picture a dead blankness. Picture a deep physical state whose meaning is still being argued by the greatest theories we have. Picture a silence that may carry the fate of expansion. Picture a missing explanation stretched across all of space, and let the thought settle gently. Perhaps the universe is not mysterious only because it contains so much, but because even when you remove almost everything, what remains still refuses to be understood. The universe's fate depends on expansion and energy. The universe's ending is not written only in the stars, but in the quiet balance between what pulls space together and what drives it apart. When you imagine the fate of everything, it is easy to picture a final scene. The last star fading, the last black hole evaporating, the last cold darkness settling over reality like ash. But cosmology does not begin with the ending as a picture. It begins with a question of behavior. How fast is the universe expanding? Is that expansion slowing, speeding up, or changing in some more subtle way? What kinds of energy fill space? How much matter is there to pull against expansion? What is dark energy really doing? And does it stay constant or evolve over time? These are not small details. They are the levers of cosmic destiny. The future of the universe depends on expansion and energy, because space is not merely a container holding galaxies. It is a dynamic part of the story, and the contents of the universe help decide how that story unfolds. In the simplest older picture, the question seemed almost like a contest between expansion and gravity. If the universe contained enough matter, gravity might slow the expansion, stop it, and eventually reverse it into a collapse. If there was not enough matter, the universe might expand forever, thinning out slowly as galaxies drifted farther apart. That was already a haunting choice. Collapse into a fiery end, or expand into an endless cold dilution. But the discovery of accelerated expansion changed the question. The universe was not merely expanding against gravity. The expansion itself appeared to be speeding up, as if a hidden ingredient were giving space a preference for widening. That ingredient is what scientists call dark energy, and current observations suggest it makes up most of the universe's total energy budget, with NASA describing it as the unknown cause of accelerating expansion, and a key reason we cannot know the final fate without understanding its nature. If dark energy behaves like a constant property of space, then the most likely long-term future is not a dramatic collapse, but an endless expansion leading toward what is often called the Big Freeze or heat death. In that scenario, galaxies outside bound groups recede beyond reach. New star formation slows as gas is used up or dispersed. Existing stars burn out. Stellar remnants grow cold. And the universe gradually loses the usable energy differences that make complex processes possible. It is not an explosion. It is not a single moment when everything ends. It is a fading of activity, a thinning of possibility, a cosmic winter so long that the word future begins to lose emotional meaning. Energy would not disappear, but it would become less available to do work. The universe would approach a state where everything is spread too thin, too cold, too isolated for the bright complexity we know. But this fate depends on dark energy remaining close to constant. If dark energy changes, the ending can change too. NASA notes that distinguishing whether dark energy is a cosmological constant, a changing field, or a sign that gravity itself needs revision is essential for predicting whether the universe lasts forever. If dark energy weakens over time, the expansion might eventually slow more than expected, and some models even allow a future reversal into a big crunch, though this is not the leading simple picture under current standard cosmology. If dark energy strengthens in a particular extreme way, a big rip becomes possible, a scenario where expansion becomes so intense that it eventually overcomes not only the distances between galaxy clusters, but galaxies themselves, then star systems, planets, and even matter's smaller bonds. That is not the usual expectation. It requires a special kind of dark energy behavior that has not been confirmed. But the possibility shows how sensitive cosmic fate is to the hidden properties of energy. A small difference in what dark energy is can become an enormous difference in what the universe becomes. This is why the fate of the universe is not just about how much stuff exists. It is about what kind of stuff, what kind of energy, and how those ingredients behave across time. Matter pulls through gravity, radiation thins and cools as space expands. Dark energy, if constant, remains influential even as matter becomes more diluted. Curvature, expansion rate, and energy content all work together. A universe dominated by matter behaves differently from one dominated by radiation, and both behave differently from one dominated by dark energy. The future is a negotiation among these ingredients, not a simple countdown, and the negotiation is still being measured. NASA's WMAP overview describes a cosmic inventory where ordinary atoms are only about 5%, dark matter about a quarter, and dark energy about 70%, with dark energy causing the expansion rate to speed up in the standard picture. But cosmology is not finished with that inventory. New surveys are measuring galaxies, supernovae, and large-scale structure with increasing precision, trying to learn whether dark energy has remained perfectly constant or changed over cosmic history. That is why missions and surveys matter so much. They are not only mapping where galaxies are, they are trying to read the future by reconstructing the expansion history of the past. The way the universe expanded billions of years ago becomes a clue to how it may expand billions of years from now. Every distant supernova, every galaxy clustering pattern, every weak bending of light by mass, every ripple in the distribution of galaxies becomes part of the cosmic forecast. Yet even with all of this, the ending is not known with absolute certainty. That uncertainty should not feel like failure. It should feel like honesty on the largest possible scale. Science can say what current evidence favors. It can say which possibilities look more likely and which require unconfirmed physics. It can rule out some simple ideas and sharpen others. But it cannot honestly pretend to know the full future before it understands the deepest nature of dark energy, quantum gravity, vacuum energy, and the long-term stability of the fields that shape reality. Even the possibility of vacuum decay, sometimes discussed in theoretical physics, reminds us that the universe's future may depend on properties of fields we do not fully understand. In that speculative scenario, if our vacuum state were not the lowest possible state, a transition to a lower energy state could in principle change the laws or particles as we know them. There is no evidence that such an event is imminent, and it should not be treated as a practical fear. But it shows how cosmic fate can depend not only on what expands, but on the deep energy state of space itself. The universe's future is therefore not one story, but a branching set of scientifically grounded possibilities. The Big Freeze is the most natural outcome if expansion continues accelerating under something like a constant dark energy. A Big Crunch would require expansion to reverse under conditions not favored by the simplest current evidence. A Big Rip would require dark energy to grow stronger in an extreme way. Other futures depend on more subtle changes in fields, gravity, or vacuum energy. The names sound dramatic, but behind them is one central truth. The fate of the universe is a question about the behavior of space and energy over time. This can feel cold at first, as if the universe is nothing but an equation slowly spending itself. But there is a softer way to hear it. The fact that the future depends on expansion and energy means the universe is still a story of relationships. Gravity remembers closeness. Expansion creates distance. Matter gathers. Radiation cools. Dark energy widens the stage. Stars turn stored nuclear energy into light. Black holes store gravity's deepest consequences. And somewhere inside this immense unfolding, life appears briefly, not at the end, not at the beginning, but during a luminous middle era when energy differences still exist. Stars still shine, planets still hold warmth, and minds can ask what the final chapter might be. That is not a small thing. If the far future is cold and thin, then the present is not ordinary. It is a rare interval of structure, brightness, and possibility. If the ending is uncertain, then wonder is not a weakness. It is the correct response. So when you hear that the universe's fate depends on expansion and energy, do not imagine only a distant scientific forecast. Imagine the whole cosmos as a balance still being understood. Matter pulling inward, space stretching outward, dark energy shaping the largest future, and every observation adding one more clue to the final direction. The ending has not been read from a finished book. It is being inferred from light, motion, distance, and the hidden pressure of empty space. And perhaps that is the most honest and haunting lesson of all. The universe may have a fate, but we do not yet know whether that fate is a slow freeze, a reversal, a tearing, or something stranger than our current names can hold. The more we learn, the stranger the cosmos gets. The cosmos does not become simpler when we understand it. It becomes stranger in more precise ways. This may be the most honest ending to any journey through the universe, because science is often imagined as a machine that removes mystery, as if every discovery closes a door, turns wonder into explanation, and makes reality smaller by naming it. But astronomy and physics have done almost the opposite. Every time human beings have widened their view, the universe has not become more ordinary, it has become more deeply unfamiliar. We once thought the sky was a ceiling of lights turning above a central Earth. Then we learned Earth is a planet, one moving world among others. That could have made the cosmos feel more understandable, but it only opened the next strangeness. The sun itself is one star among hundreds of billions in a galaxy. Then the galaxy became one among billions. Then the visible universe became only the portion light has been able to reveal. Each answer did not end the questioning. It enlarged the scale on which the questions had to be asked. The more carefully we looked, the less the universe resembled the simple stage our senses evolved to handle. It was not centered on us. It was not static. It was not made mostly of the luminous material our eyes notice. It was not filled with stars arranged randomly, but structured into a vast cosmic web shaped by gravity and hidden mass. It was not born as a neat explosion into empty space, but emerged from an early hot, dense state. whose afterglow still surrounds us in faint radiation. It was not perfectly transparent at first, not calm in the way a quiet room is calm, not empty in the way a box becomes empty after you remove its contents. Again and again, reality turned out to be less like common sense and more like a set of hidden rules patiently revealing themselves through evidence. And that is the remarkable part. The strangeness is not a failure of knowledge, it is what knowledge found. We did not invent dark matter because we wanted the universe to sound mysterious. We inferred it because galaxies and clusters behaved as if unseen mass was shaping their motion. We did not invent dark energy as a fantasy. We named it because cosmic expansion appeared to be accelerating, and something in our model had to account for that. We did not imagine black holes only because they were dramatic. We found compact objects, gravitational waves, hot disks, stellar orbits, and shadows that match the predictions of extreme gravity. The universe becomes stranger because our measurements become more disciplined. Mystery does not survive despite science. It often becomes sharper because of science. Before we measure, a mystery is fog. After we measure, it becomes an edge, the clean outline of what we still do not understand. And the cosmos is full of those edges. We know the universe is expanding, but the nature of the energy driving its acceleration remains unclear. We know ordinary matter forms stars, planets, and bodies, but ordinary matter is only a small part of the cosmic inventory. We know quantum fluctuations may have seeded the larger structures, but the earliest physical conditions remain difficult to probe directly. We know the vacuum is not the simple nothing our intuition imagines, but we do not fully understand why its gravitational effect is so small compared with many theoretical expectations. We know black holes connect gravity, temperature, entropy, and information in unsettling ways, but a complete theory uniting gravity with quantum physics remains unfinished. The deeper we go, the more the universe seems to place its hardest questions exactly where our best theories touch, but do not yet fully merge. That is not discouraging. It is the living frontier of understanding. If the universe had become completely familiar after the first telescope, then curiosity would have been a short flame. Instead, every new instrument has made the flame stranger and brighter. Radio telescopes revealed a sky full of invisible signals. Space telescopes saw ancient galaxies and newborn stars hidden from ordinary sight. Particle detectors caught ghost-like messengers from violent events. Gravitational wave observatories listened to space-time itself, ringing from the mergers of compact objects. Each tool opened a sense we did not biologically possess. Human eyes are narrow instruments, tuned to a small slice of reality. The universe speaks in radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, neutrinos, cosmic rays, gravitational waves, motion, chemistry, and statistics. To know the cosmos is to admit that the body was born with only a few windows, and science is the art of building more. But more windows do not always make the house simpler. Sometimes they reveal rooms you never suspected were there. The same pattern appears in scale. On small scales, the world of particles refuses to behave like miniature clockwork. On large scales, the universe refuses to behave like a simple eternal stage. Between them lies the ordinary human world, the narrow band where chairs feel solid, time feels steady, and space feels obvious. We live in the middle scale, and because of that, we mistake the middle scale for truth. But the cosmos keeps reminding us that intuition is local. It works well for walking, touching, throwing, building, and surviving. It does not automatically work for the birth of space-time, the interiors of black holes, the behavior of quantum fields, or the fate of galaxies beyond the horizon of future communication. This is why learning astronomy can feel like a gentle form of losing certainty. You do not lose reality. You lose the small version of reality you inherited without noticing. You begin to see that empty may not mean empty, dark may not mean absent, far may also mean old, straight may depend on geometry, and visible may only mean reachable by light. Even the word now becomes softer when applied to distant galaxies. Even the word edge becomes unstable when applied to the universe as a whole. Language, which feels so strong in daily life, begins to stretch under cosmic pressure. Yet this stretching is not meaningless. It is how the mind grows. A child learns that the horizon is not the end of the world. Humanity learns something similar about the sky. The horizon keeps moving, not because truth is escaping us, but because truth is larger than the first boundary we drew around it. And perhaps the most beautiful lesson is that the universe's strangeness does not make it less real. It makes reality richer than expectation. A false mystery asks you to stop thinking. A real mystery asks you to think more carefully. The cosmos does not demand belief in exaggeration. It rewards attention to evidence. It does not need lies to be astonishing. The facts are already enough. Ancient light fills the sky. Galaxies arrange themselves into enormous networks. Stars make and scatter elements. Black holes bend time near their horizons. The largest share of cosmic influence is hidden in forms we do not fully understand. And the future of everything may depend on properties of space and energy still being measured. None of this is decoration. These are the pillars of the world you inhabit. You live not beneath a simple ceiling, but inside a universe that has spent billions of years turning simplicity into structure, structure into stars, stars into elements, elements into planets, and planets into observers capable of being confused by the whole process. That confusion is not a flaw. It is a sign that the mind has reached the edge of its old map. And at the edge of an old map, two things can happen. You can retreat into simple stories, or you can let the unknown teach you a better kind of humility. The more we learn, the stranger the cosmos gets, because learning removes the comforting illusions first. It removes the idea that we are central, the idea that what we see is all there is, the idea that emptiness is simple, the idea that time and space behave everywhere as they do in your room. But after those illusions fall away, something deeper remains. Not despair, but intimacy. You are not outside this strangeness looking in. You are made from it. Your atoms belong to cosmic history. Your body depends on laws written long before Earth. Your thoughts are a late event in a universe still not fully understood. So when the cosmos becomes stranger with every discovery, let that strangeness feel less like distance and more like invitation. It means there is more to learn, more to question, more to become honest about. It means the universe has not been reduced to a solved machine. It is still open, still layered, still surprising the minds it created. And maybe that is the softest conclusion. Knowledge does not end wonder. It gives wonder a sharper shape, a deeper voice, and a wider sky to move through.